Okay, so once again, good morning, everyone. Before we start what we have today, does anybody have any question about what we did yesterday? Maybe after going back and going through it, there were some things that were not clear enough yet. We can start by just answering some questions and then see how we go from there. Any question? Any questions so far? No question. Okay. So I'll just need like 5 people. So just tell us what they understood yesterday. Yeah, 5. Should it be?
Let's check out how far.
Okay.
There's no mass that is too hard for what you don't name. We finished Jap yesterday. No wonder these guys are fresh. You guys finished Jap yesterday.
Yeah.
couldn't finish this out. From
That-
this show, we started from that.
So they were a lot.
You guys the money going now.
Okay. Okay. So 5 people, right? Should it be based on volunteering, or should I pick? Or should I throw dice? Let me throw dice. Okay. I will. What will I use?
Explain what your ship from yesterday's class.
Okay. Sorry, Roima, you were not in the class yesterday. Were you able to? You've not been able to. Please just. Okay.
Tried it.
Okay, sir, please. One thing you learned in the last class. I learned about error amplification, the error amplification property of a polynomial. That aside using a polynomial to just evaluate, you can, when you get a polynomial, you can use it to evaluate at any point, and then that gives us like the ability to do the blow up, to like blow up the instead of just being within a bound, we can blow it up and then test for various values across the board.
Okay. Nice. So does any other person want to try?
I learned about representing your matrix of the curve and converting the matrix into a polynomial.
Okay. So that is kind of like learning about representing data as a polynomial. Okay. So matrix is just one form of data, right? So it can be an English text, right? That you convert to bytes, right? And interpolate, get a polynomial. And if somebody wants to reconstruct that text or that message, the person just needs to evaluate the polynomial at a certain number of points, and then say based on the encoding scheme that was used, you decode it back and you get your message. Does that make sense? So just think about it abstractly. That is the idea, right? So when we hear of ZK email, how many of us have heard of ZK email? Yeah. So we can just think about it as something similar, but there are a lot of other moving parts. Right. Okay, so any other person?
One of the simple thing I noticed was increase your chances, your success, chance of success by improving your level.
Yeah, nice. So that's 3, right?
4.
4.
I think the thing I learned yesterday was the block factor and how it affects the over time and must check through the entire time. How you have to use how the time are affected. So if you want to have a larger time space, how it increases your likelihood over time.
Yeah. Okay, so basically how the blow factor increases your space complexity. Okay. Okay, makes sense. That's a good one. So, would there still be any need for me to run over it? Or we can just maybe look at some check, and after some check, we can go back and revisit.
Please go over the one that maybe just briefly go over that dynamic matrix points.
The matrix.
Points like dynamic
Okay. Like representing, like going from representing the matrix as.
to the multi-linear
Okay. Okay. My listen is not. Can you guys just give me a minute? Let me see if I can get the writing gear. So in case we need to do some writing. Yeah. Mine is not here yet. Okay. So this is a good place to start. Is this a good place to start?
Yes.
Okay. So firstly, we have like the different people in the network, right? A, B, C, D, E, F. Those are different people in the network based on their, let's say, their names, right? But then we want to represent, like, we need a way to represent them. It's kind of like giving everybody an ID, right? So A to H, that should be 8. That means we have 8 people in the network, right? And we need to give each and every one of them an ID, right? So that we can forget about their name and address them by their ID. Basically, all we need to do is just give the first person 0, ID of 0, right? Second person, ID of 1. Third person, ID of 2, up to the last person. The last person will be ID 7, right? If we are going from 0 to, we want to give 8 people an ID, but we are indexing from 0, right? So the last person will be ID 7. So if we now convert each person's ID to binary, that's basically what where we talked about the labeling. but it's just converting each person's ID to binary, right? So when we want to address a person, we don't need to address the person by the person's name again. We can address the person by the person's ID, and not just addressing the person by the person's ID, but address the person by the binary representation of the person's ID. Okay.
You can actually adjust
The graph, right? Don't
Not
mind.
even that one, like. So, I'm coming, just let me.
Okay.
When I did it in the copy, I
Okay, you have.
yes.
Okay.
Sorry, I
Okay. Can sit. Maybe I'll go for now.
yeah.
Very crooked representation.
So this works.
I think this works. Thank you. Come in the more, please.
Can you reduce the size?
No, I think it's okay, right? Okay, yeah. Let me reduce the size a bit.
I think the previous labeling was now that you
Was
remove that
better.
label,
The font size.
Yeah. Mm. I hope this works. I think it should. Right. Okay. So for each person, you give the person an ID, right? And then convert the person's ID to binary. So anytime we want to address somebody, we don't need to know the person's name again. All what we need to know is the person's ID. Right. And with that, we now go ahead. We're trying to generate a polynomial that can tell us if there is a connection between two people in the network. That's kind of like the basis of what we started building on. Right. So first of all, we represent this, like each person or each pair of people in the network, and if there's a connection between them, we represent it as a point value representation. So this is the point, and this is the value. Right? It makes sense. But this point is still made up of like two different people. We're combining them together to know if like there's a connection between the both of them. Yeah. So this is for like if I want to check if there's a connection between person A and person B, this will be the ID for person A, and this will be the ID for person B. And then the goal is that we want to generate a polynomial such that if we evaluate that polynomial at persons A and person B ID, we are going to get a 1 or a 0 if there is a connection between them. Does it make sense up to this point? Okay. So normally, let's say in primary school, when we want to plot a graph, what was the graph we commonly plotted was like a univariate, the graph of a univariate polynomial. Thank you. So where we have the x value and the right and the y value, right? So you have a function f of x. Let me okay. So in primary school, when we want to plot a graph, we usually have like a polynomial, let's say serious. And when we have a function f of x equal to y, this is a univariate polynomial. Why? Because we have just one variable, x, right? And we can remember, like, if you're plotting a Cartesian graph, you have your x and your y coordinates, right? This is your x, or you can call it negative x, and this is your y, right? And negative y, positive x, right? So for each value of x, there should be a corresponding value of y, right? So let's say you have f of 3 equal to 5. Hope you guys are seeing the handwriting. Okay, so say you have like f of 3 equal to 5. That means if you pass 3 into this function, let's say 3 is at this point, and let's say 5 is at this point, this will be the point on the Cartesian graph, right? And let's say you have f of 2 equal to, let's say, 4, and f of 1 is equal to let's say 3. So this is 1, this is 2, and this is 3. So f of 1 is equal to 3. I just call here 4 and 3. So f of 2 is equal to 4, right? So this is what it's going to look like, right? And then you're now meant to like draw a, in this case it's a line, but in some cases it may be a curve, right? You draw a line that passes through it, and that equation, this f equation, is the polynomial of this curve, right? You can also evaluate this polynomial at, let's say, 1 million, right? And whatsoever thing it gives you, you can still come on this graph and plot it, let's say at 1 million, whatsoever value it is. You can still plot it on this graph. Do we agree? So so in this case, this value of x is not just one variable like we had here, that was just one variable. So in this case, it's multiple variables, right? It's multiple variables. So we can have something like f of, let's say, okay, a, b, c, right? In our case, like d, e, f equal to either a 0, a 1, or equal to, let's call it y, right? Just like we had here, f of 3 equal to 5. 5 is the output, is the value. 3 is the input, which is the variable, right? So in this case, in this other case now, since we have multiple variables, when we want to evaluate this polynomial, we need to define a value for each of those variables, which is in this case, these three variables a, b, c can be used to indicate the label or the ID for person, for the first person, and this other three is used to indicate the ID for the second person, right? Does it make sense up to this point? It makes sense, right? So if we want to check if there is a connection between person A and person B, what we do is we get the ID for person A. Let's say the ID for person A is 000, right? And the ID for person B is 001. So what we'll be passing to this function is basically f of A will be this 0, B will be this 0, C will be this 0, right? So 0, 0, 0, and then it's time for person B, right? 001, where f is 1, right? So that's 0, 0, 1. Does it make sense? So if we want to find if there's a connection between person B and person C, can somebody tell me between person B and person C? Can somebody tell me the inputs to the function f? Okay, what is person B's ID first? 001, right? And what is person C's? 0, 1, 0. So what will be the inputs to our function? 0, 0, 1, 0, 1, 0. Right.
Sorry. Is it fair to represent a binary digit like this? It's command.
With commas.
Is it fair to
In this case, we can. In this case, we can. Why? Because we are attributing each of these values to a variable. So that's why we are going about it. Right, okay. So does it make sense up to this point? Sure. Okay. So, Rohima, are you sure? I know, like, you were not here yesterday, but say from where we started, does everything make sense up to this point?
Yeah.
I'm still going to review it for you. Okay. So now we can see a way of checking if there's a connection between two people in the network. Right. So if we want to check all the possible pairs of people in the network, all possible pairs of people in the network, how do you think we can go about that? This is a lot, right? So let's create a network of 3 people. Let's just like create an example network of 3 people. We have person A, person B, and person C. Right? So these are just 3 people. We give person A an ID of what? No, not 0, 0, 0. An ID of 0. Let's think of it in decimal now. Like, I also want us to see why is it 0, 0, 0? Why is it not just 0 and let's say, why is it not 0, 0, like for this first case? Why is it not just 0, 0, 0, 1, 1, 0? I want us to see, like, so we give the first person a decimal ID of 0, right? We give the second person a decimal ID of 1, right? We give this person a decimal ID of 2. 2 is the biggest ID in this case, right? So if we convert 2 to binary, what's 2 in binary? 1, 0. 2 in binary is 1, 0. 1, 0 in binary, right? 1 in binary is 1, right? But since we have 2 here as 1, 0, which is represented with 2 bits, that means we also need to represent B with 2 bits. So it will be 0, 1. Does it make sense? And A with ID 0 is 0 in binary, right? But since the maximum bits we have to represent any node on this graph is 2 bits, so we are going to represent it as 0, 0, right? So we can basically substitute anywhere we see A, we can basically substitute it with 0, 0. Anywhere we see B, we can substitute with 0, 1. Anywhere we see C, we can substitute with 1, 0. Okay.
So are we just the one setting the number of bits, or there's a law that says that the highest number of IG is going to determine the number of bits of the remaining ones?
No, it's kind of like a law. in binary. Like, you can't say you're writing a program. If you're writing a program, you can't store 1000 in a U8, right? If you want to store 1000 in a U8, it will panic or it will overflow. Why? But what does a U8 even mean? Okay, a U8, good and fine. We are going out of this thing now, but I think it's necessary. Right. So, a U8 is an unsigned integer, right? Good and fine. The U here stands for unsigned. What does the 8 stand for? 8 bits. Right? So, we have an unsigned integer that's 8 bits. So basically, we have, let's just define 8 bits. Is 1, 2, 3, 4, 5, 6, 7, 8. 8 bits, right? So, and we know a bit can either be a 0 or a 1. A bit can either be a 0 or a 1. What is the difference between an unsigned integer, or what is the difference between a U8 and an I8? One can be signed, the other cannot be signed, right? Unsigned means we can take it as a positive. Like, we cannot represent a negative number with an unsigned integer, right? But why?
Because there is no space to store the sign, or the way unsigned integers are stored. Compiler, there is no space to store the sign.
Yeah. Why can't what was the question again? Yeah. So why can't you store a negative number with a U8?
Why can't you store a negative number?
Is it because of the name? There was a reason they gave it the name. Do you know the reason they gave it the name? Unsigned.
All the bits are used to store because in signed integers, the first or the highest order bit is used to store the sign. But in unsigned integers, all the bits rather are used to store the values of the integer. So you cannot store the sign.
Yeah, you got it. So basically,
What did you say?
I'll go over it. Basically, what's important in the U8 there is the 8, right? When you see a U8, for the compiler engineers in the house, or like when you see a U8, the system allocates 8 bits, right? That's what's important. 8 bits. Information like so I say barest minimum that we can reduce information to is bits, right? Either a 0 or a 1. But it may change in the future, right? It's already changing, right? With the whole quantum stuff. So we have 8 bits of space, hardware, right? You know, a bit is, you can think of a bit as a bulb light. So when it's on, it's 1. When it's off, it's 0. So that's basically when we allocate like 8 bits to store an information, we are basically saying, okay, give me 8 bulb lights. Does it make sense? So now the U, where the U and the I come to play is in how we store information in those 8 bits. In the I case, integer, when we say an integer, it may be a positive or a negative integer, right? And we need a way to tell that it's a positive or a negative integer. And that is what, in the I8 case, the first bit is used for that information to store if it's a positive or a negative number. So that means, since this first bit tells us the sign, either plus or minus, the only number of bits we have to represent the information we want to store is 7, right? Which is this remaining 7. We have used the first bit to store the sign, either plus or minus. So any other information we want to store can only be stored in 7 bits, right?
That's the
sign
sign
is a part of-
integer.
That's what it's
Yeah, that is what I'm saying for I8, yes.
No, are you saying that for grades, the first bit is not to recognize
The sign, yes.
No, it's just for the
You can store like 8 bits of information, yes.
I guess that's why for I8, it's not complete.
It's not exactly. So if like the maximum number you can store in a U8 is higher than the maximum number you can store in an I8. It's almost like half. Yes, it's almost half the information. Is it making sense? So you ask, why is it like almost half the information? Let's ask why. Like that question, why, is very important. Anything you're doing, always be asking why.
I think that
Why?
single bit that is left out for the sign to reduce it.
Yeah. So why? The question why is like a very important question in life. Why am I learning ZK? Why am I here? So generally, not just with respect to this. So the question why is a very important question in life, and whenever you see something, try and ask why.
Why did you never do this to us?
Why do never do this?
That would be answer.
Like, with group now, that's is 2 is part 7. That's 128. So when you remove 128, what you have there is 255 plus 6, 255. So what
So-
you're left with is now 127.
Okay. So what I'm trying to like why is it that just this one bit reduced the number we can represent by half?
Are we answering?
Do you know the answer?
Yeah.
Can you attempt the question?
Since it's binary, right? You should have like 0, 1, 2, 3, 4, kind of power expansion this thing. So if one bit is left out, that means let's say this is 8 bits, right? And 0, 1, 2, 3, 4, 5, 6, 7. So it's supposed to have like 2 raised to power 7 each of like max. If that one is left out, then we're going to have something lesser than that. So like I'm trying to convert the binary now. it's like decimal value. So if that bit is left out, then
Yeah, you got it, but I don't know if everybody understood. Yeah, you got it, but I don't know if everybody understood. Well, let me see if I can try to explain it in a way that everybody can follow.
Sorry. Why are you trying to explain? Can you just...
Okay. You know, when we have an I8,
Yeah.
we use the first bit to represent the sign, and then that means we have like just 7 bits of information left, right? When we have a U8, we don't store the sign because U means unsigned. That means any number is always going to be a positive number, right? So that means we have this extra bit to ourselves, right? We can also store information in it.
Okay, for the unsigned.
Yes, for the unsigned. So now, if we now look at, okay, this U8 is big. Let's break it down to, like, let's go maybe a U3. It doesn't exist. Like,
Okay.
there's no U3 in any language,
Yeah.
but just to explain this, let's look at a U3, right? Does it make sense? So when we say a U3, what does it mean? We have 3 bits, right? So we have 3 bits to represent information, right? So since we have 3 bits, we're still going to look at the I3, but let's look at U3 first. How what is the maximum number that can be represented with a U3? 7. And what is 7? In 111 in binary, right? So if I tell you to mention all possible combination of numbers that can be represented with 3 bits, all possible combination. So we have 0. Okay, they said the maximum is 7, right? Thank you. So we have like 0, 1, 2, 3, 4, 5, 6, 7. 0, representing 0 in 3 bits is 0, 0, 0. 1 is, okay. Sorry. 1. Wait. Sorry, 6. Six is
110.
Do we agree that this is all possible combinations?
Yeah.
Do we agree? So I can't call a combination of 3 bits that is not here. Is that what you're trying to tell me?
Yes.
I can't call a combination of 3 bits that is not here. Okay, what of 1110? Okay, actually, you guys are right. Right. So this is like all possible combination of 3 bits. And we can also think of it this way. Since we are working with binary, that's base 2, right? and we have 3 bits. So we can represent 7. 7 is the maximum number we can represent, but the total amount of information we can store is 8, right? 0 to 7. 0 to 7 is 8. And 2 to the power of 3 is 2 to the power of 3 is 8. Does that make sense? So when I was saying 2 to the power of 6 yesterday and 2 to the power of 9, are you people able to draw any connection between that? So okay, let's go back to our
What about I3? Let's see what I3 is.
okay, I3, okay. So this is U3. So for I3 we have 3 bits, right? And we're using the first bit to store the sign. So normally if it's a positive is a 0 and a negative is a 1. Yes. The other way. No, it's not the other way. So when we see an I3, we check the first bit. If the first bit is a 0, that means it's a positive number. If the first bit is a 1, that means it's a negative number. Okay, now we know the sign. What is the number? We can see that since we've dedicated this first bit to the sign, we only have 2 bits to represent information. Right? And what are the possible, or what is the maximum number that can be represented with 2 bits? With 2 bits. 3. Which is 1 1 in binary. Right. So the maximum number that can be represented with a bit is with a series of bits is when all the bits are on. Right. So for U8, the maximum number is 1 1 1 1 1 1 1 into 8 places. For U32 is 1 1 1 1 into 32 places. For U64, 1 1 1 into 64 places. That's the maximum number that can be represented. Does that make sense? And then you see a solidity where they use U256. Right? What does that mean? That's like 256 bits. Yeah. U256 max. That's 11111 into 256 places. Right. Okay, so now we can see that the maximum number we can represent with 3 is 1 1. With 2 bits, sorry, is 3, which is 1 1. Makes sense? Okay. So next is that we now want to see all possible combination of numbers we can represent with 2 bits. So that's 0 to 3, right? So we have 0, 1, 2, 3. 0 is 2 bits, 0 0, right? 1 is 2 is, and 3 is, right? So we can see that we can represent only 4 numbers, that's 0 to 3, with 2 bits. Right? We can represent 4 numbers with 2 bits, but we're able to represent 8 numbers with 3 bits. Does that make sense? Do we see the jump? Just because we took away 1 bit, we halved the number of possible numbers we can represent. Just because we took away 1 bit.
Because when they are like those ones are like positive, so the negatives.
Yeah, I'm coming to that. I'm coming to that. So now, in this case, this is just like for 2 bits, right? But we can remember that we are dealing with an I3, which means we are still working with 3 bits of information. So we still need to put that 3rd bit. And what does this mean based on? So this basically means 0 or positive 0, positive 1, positive 2, positive 3. Right? And then still the same information, like 0 0 0 1 1 0 1 1. If we use 1, this is negative, okay, this is positive 0, positive 1, positive 2, positive 3. It's negative negative 0 if there's anything like that. Negative 1, negative 2, and negative 3. So we are still able to represent, with 3 bits, we are still able to represent 8 units of information, right? But then the maximum number that we can represent is much lower in the I32 case. So in the I3 case. So in an I3 we can represent numbers ranging from -3 in an I3 to +3.
Yeah, but I thought it should be -4.
-4.
What of in a U3 then?
That's in the U3. It's 0 to 3, so the highest. But normally it's 4, but the highest is 3.
Yeah, but the highest is 3. Does it make sense up to this point?
Yeah.
As if some people are lost. Is anybody lost? Does anybody have any question?
I have a question. So I'm thinking, would that be any time when we are going to have 1 0 0, like, does 0 have negative sign in front of it? Just,
Like, okay, 1 0 0.
yes,
0 does not have any sign, right? But this is just
the representation.
this on the computer, like we can think of it like on the hardware level.
Alright.
You get? So it makes sense. So why I went about all of this, right, is just to explain why when we say all possible combinations of a number with a certain amount of bits, we can instantly know the number of possible combinations. Does that make sense?
Yes.
So if I say what is all possible combinations of U16, all possible combinations of U16, 2 raised to the power 16, right? Good. And if we can represent all possible combinations, that means we can represent all possible combinations of people in the network. Do we agree? We agree, right? Because there's no connection in the network that cannot be represented with all possible that won't be within that, like, the range of all possible combinations. It makes sense.
I don't agree with that, but he was right. There's no minus 0. It's actually minus 4. Like,
-4.
there's a go out
Okay.
calculation
Probably. That means they use like 100 for -4 to represent -4.
Then it counts -3, -2, -4.
Okay. Well, the main thing is, do we understand the intuition? The intuition is what is important. Right?
So I think the possible combinations is 2 raised to the power the number, while the maximum number is like 2 raised to the number
-1. Yes. Yes.
We can explain why the science exam stores out of the paper. I don't know if you
Okay. No, it's actually because we have just 2 bits. As opposed to 3 bits in the U3. In the U3, we are not using this first. In U3, we can also store information in this first bit. But in the I3, the information we are storing in the first bit is the sign. So we basically take away that first bit and use it for the sign. Then what we can use to represent a number is 2 bits.
Okay, so when you mean half, you don't mean like half of like the
Yeah, not half of the bits.
okay.
Like the number, the maximum number, not the maximum number of information. No, it's different. There's the maximum number of information, which will always be 8. The maximum number of information will always be 8, right? But the maximum number is 3. And 3 because 3 is the maximum number we can represent with 2 bits. I know it can be like kind of confusing. The highest decimal number.
So I have a question. In our presentation of what we're doing, like the whole graph of network that we're trying to represent and check how they relate to each other, and we have been using is there any time we are going to make use of the sign integers, that's the integers, or they are all going to be positive, like we are always going to use the 8, like I don't know.
Yeah, like when we give You can't give somebody a label of minus. You can't give somebody an ID of -3.
Yeah.
Yeah. So it's always be positive. Does I don't know, does it make sense?
Yes.
It's not so clear, you don't
You know,
think.
the other time you say that why is it that you can store more data in UAs, then you can store half of that data.
Okay, sorry, maybe it's the way I worded the question. But it makes sense now, right? The data will always remain the size, same size, but let's say the decimal number now will be half. So maybe after this, I think maybe after this we can still go back and look at like U8 max and I8 max, or not just U8 and I8 but other types too.
So when you said to only be possible, is there as regard to this or is it a general?
Always be no, just with regards to this. Yes, just with regards to this. That is the labeling. That is what you're talking about. Right?
I was thinking what you meant was for everything we be doing.
Okay, no. Just with regards to it.
You said 3 is the maximum. 3 is the maximum number you can store in the right?
Yeah.
For an I2.
For an I3, sorry, yes.
For U2, right?
No. For an I3. For an I3, 3 is the maximum number you can.
Yeah, for U2 is 7.
For U3 is 7. Because you can use that first bit, you can use everything. Does it make sense? Are we clear up to this point? Another stupid question. What is the maximum number we can, like, what is all possible combinations of the total? Okay, what is the total?
Yes.
It's still the same thing. Yeah. Like all possible combinations of U32. So it's about 32, right? But you know, it's not just a number, like there are different numbers that total to that.
Yeah.
Just like this. Like 1, 2, 3, all these numbers, when you total it, that is what now gives us that max. Makes sense? Okay.
Can we say like for an assigned the total maximum number you can have there is like 2 raised to power let's say 2 raised to power that number minus 1.
Yes, 2 raised to the power. The minus 1 is also in the exponent.
But for a unit to be like 2 raised to power that number minus 1,
Then minus 1. Yes.
What's that?
Yes. I know what he said may.
So I think what we need to understand is there's possible combinations and maximum decimal number. So we don't confuse the formula for the possible combinations with the formula for the maximum decimal number.
Exactly. But the idea of this is just to give us the intuition. We may not get it, like we may not get everything now, but if you have the intuition, you can always say rederive it. Rahim, are you with us? Are you sure?
What I always thought before was that units usually like have more numbers than units because it have like things and it's not supposed to be precisely that way. Negative end of the spectrum, positive. So I think that was like double of the units. But now I
but you understand why now, right?
But I don't, it's still in, I feel it's still in line because it was what I thought also, but then the explanation today made it better because, you know, the negatives, the int has negative and positive, but uint is using up that space for negative to give more digits. So I think with this now, it makes it, because the first bit now is used to represent negative or positive, that is the sign, leaving out the remaining for calculation. So because of that, the power is different. So for unsigned, it is 2 raised to power that number. Then for signed, that is, it will now be 2 raised to power that number minus 1, which will give that half difference between them. So I think it's still in line.
Yeah, but it's clear to you now, right?
Sure.
Okay, so there was a reason I broke it down to U3, right? Because of this network of 3 people. So now, if I say I want to check all possible pairs of people in the network, does it make sense if I just, like, let's say in this case we have 000110, right? That is the ID for the 3 people in the network. So if I want let's say a function so if I want a function so if I want a function, say f, that can check if there is a connection between 2 people in this my small network of A, B, C. Right? We know that each person has a 2-digit label. Right? So can I say something like A, B, C, D? This makes sense, right? So if I want to check, say, all the people in the network that are connected, I can just pass in like all possible combinations of 4 bits of numbers that can be represented with 4 bits. That is, there are 2 to the power of 4 possible combinations. But if I now want to know, like,
That's for if there are 4 in the network of
no, like in this network of 3 people.
So the ABCD is for
So the ABCD, like, this will be used to represent the first person. This will be used to represent the second person. It makes sense. Okay. So will I be correct to say that there is 2 to the power of 4 possible combinations of pairs in this network? Correct, right? But if you now want to know the pairs that are actually connected, that will now be finding all the pairs that after evaluating we get 1. Makes sense. So if we want to find the total number of connected pairs, all we need to do is do a running sum. We do a running sum of all evaluations. Does that make sense? We do a running sum of all evaluations. That's if we evaluate, let's say in this case 2 to the 4, right? Let's say we have 4 bits, so 3, 4. And then we just duplicate this and change the first bit to 1, right? But what does this check if we evaluate this function? Like if I pass in this to this function, what am I trying to check?
If there is a connection between
Yeah, who am I trying?
A.
Between A and A, right? If I pass in this, I'm trying to check if there's a connection between A and B, right? If I pass in this, A and C, this, A and D, but there's no D, right? Yeah, but we still check it. A and D, right? And what? Okay, this one will be B and A, B and B, B and C, B and D, right? So if we want to continue, that will be like 1. C and A, C and B, C and C, C and D, D and A, D and B, D and C, D and D. So we can see
I'm confused how you are matching with the letters.
the letters.
Yeah.
Okay. The first two. This 1 0, right? So this 1 0, that's C. Yeah. 0 0 is A. It makes sense, right? We see that by going through this, we're able to call all possible combinations in the network. So now if we evaluate and we get a 0, that means there's no connection. If we evaluate and we get a 1, that means there's a connection. We evaluate, say we get a 1. So when I say a running sum, is that we evaluate, we get the answer, and we keep accumulating. We evaluate and accumulate, evaluate, accumulate, evaluate and accumulate. For everywhere there is 0, it will not add to the total number of connections, right? But if there's a 1, meaning there's a connection, then it will add to the total number of connections, right? Does it make sense? So after doing, say, a for loop, a for loop, a running sum, right? Evaluate this polynomial at all these possible points. The total number we are going to get from the accumulated value is going to be the total number of connections in this network. Does it make sense? Are we sure? Do we have any question up to this point? Any question up to this point? No question, right? Okay, let's go back to our slide. So based on what we've explained, does this make sense? What we explained was just this so I say this polynomial A that checks if there's a connection between two people. Right? And now we're trying to check if there's a triangle in the network. Right? So we check for the first two people. We check for the second two. We check for the last two. You know, this equation is meant to give us a 0 or a 1. 1 if there's a connection between these two people, and a 0 if there's no connection. Right? Same thing with this one. And same thing with this last one. But if any of this... Hello? Are we together? If any of this is 0, it basically zeroes everything out. So like 1 times 0 times 1 is a 0. 1 times 1 times 1 is the only thing that can give a 1. You can think of multiplication as and. Right? 1 and 1 and 1 is 1. Like when we're talking of like Boolean algebra. Right? So 1 and 0 and 1 is a 0. Right? Okay. So does it make sense up to this point?
Yeah.
So but now we now have like a polynomial that, should I say, we represent this as just one polynomial. So we're trying to check if there is a triangle in the network. Right? So we have person X, person Y, and person Z. And since we have 3 people, and each person's ID is bit, each person's ID's bit representation is 3 bits, right? What will be the possible combination, the total possible combination of 3 people in the network? 2 raised to the power of 9. Why?
Because each person is made up of 3 bits and 3 times 3.
3 times 3 is 9. Is that clear to everyone? So, we know dealing with it here, it automatically deals with like the separation. This internal separation happens automatically, right? All we just need to focus on is this. Then internally, it assigns the first 3 bits to X here, the second 3 bits to Y, the first 3 bits to X, the last 3 bits to Z, the second 3 bits to Y, the last to Z.
Can we say that the running check, what it does is like, okay, this is like the left hand side is a polynomial of the multiplication of another polynomial.
Exactly. So, if you're not thinking of this, you start like, those are comfortable with proof theory. Like, it means this polynomial P is equal to A of xy times A of xz times A of yz. If for any reason we pass in the same values to these 2 half of the equations and they give different answers, then there's a problem. Does it make sense?
Yes.
I'm not sure it makes sense for everybody.
What you're telling us is
No, I'm just that's not it, but it plays a part. It's just the intuition that I'm trying to like chip to you guys. The
So what part
intuition.
does the A play?
A
Yes.
A there is the polynomial that checks if there is a connection between two people.
So like it's a smaller polynomial because the P also
Yeah,
is
it's a smaller polynomial.
P is like
P is a larger polynomial. But what we're trying to say is that after doing the multiplication and you say you get a polynomial, right, which is P, that polynomial should still be equal to, if you multiply, like if you don't do the outright multiplication, right, you just take A, evaluate A,
Yes.
and you evaluate A with these values, evaluate A with these values, and evaluate A with these values, and then the results you get from these evaluations, you multiply them together to get a result. That result you get should also be equal to P, where P is the polynomial you get when you multiply the A polynomial, like
Like when you just merge the polynomial.
the polynomial itself without evaluating it. Exactly. I don't know if it makes sense. Huh? You need explanation, alright. Okay, so what I'm trying to say is that we have P of x, y, z, right, equal to A of x, y times A of x, z times A of y, z. Let's say A is a polynomial. Which polynomial should we use? X minus 2. Right? A is a polynomial x minus 2. And like now it's meant to be maybe x y plus something something something, but I'm just removing the y factor for now, just to explain this, right? So let's just say A is a polynomial x minus 2, right? And P is equal to, okay, let's say we're going to be doing, these variables are different, right? So we'll just unify x, let's say x comma y, we're going to call it x. X comma z, we're going to call it y. And y comma z, we're going to call it z. Okay, so this is a polynomial A, right? So we can say A, right, evaluated at x times A evaluated at y times A evaluated at z should be equal to P. Does that make sense? Where this x here is this x, which is this pair. Y here is this y, which is this pair. And z here is this z, which is this pair. Right? So, what we're now trying to say is that if So P will be a polynomial in three variables, right? X, Y, Z. Does it make sense? Which will be equal to A of X times A of Y times A of Z. Right? So let's say A is X minus 2 now. We are giving A, like, we are defining the polynomial A. So that will be let's say A of X. Right? So that will be X minus 2, right? Times Y minus 2 times Z minus 2. Does this make sense?
Yes.
A of X is equal to X minus 2. Or maybe let me use what should I use? No, X not will still be confusing. Maybe K, right?
Yeah. Right.
Ah, right. So K here in this case is X now we are substituting. So which means if we put X here becomes X minus 2, right? Here is Y, so it becomes Y minus 2, right? And here is Z, it becomes Z minus 2. But yeah, so what we're trying to say is that if we multiply these three guys, right, we are going to get a polynomial, right? Should we multiply? So let's say right, so that's xy minus 2x minus 2y plus 4, right? And then we're still going to multiply with this guy, so that's z minus 2 so this will give us minus 2xz minus 2yz plus 4z minus 2xy. Sorry, is everybody following us? So minus 2xy plus 4x minus 8. So is there anything we can factor? So we can think of this polynomial as the P polynomial. So this is P of x, y, z. Makes sense? And what we're trying to say is that P of x, y, z, which is this polynomial, should be equal to this. True or false? Should it be equal? It should be, right? So, is everybody with us?
Yes.
Are we sure? Huh?
You're losing me.
Yeah. Okay.
You're losing me.
Okay. Ask Hank. Let's bring you back. Where exactly?
Not because I left, I came back.
Oh, you left.
I stepped out.
Oh, I'm sorry. So where did you?
I came back to this formula.
Okay. Were you here when we defined this? I think let me just start from here. I think from here you should. You can remember this equation from yesterday. You can, right? So what we're trying to show is that these two polynomials should be equal. P of x, y, z and a of x, y times a of x, z times a of y, z. They should be equal. How can we prove that they are equal? First of all, we just created an arbitrary polynomial a, which we called k minus 2. And a of k equal to k minus 2. Right? But we note that a here takes two values. The value for x and the value for y. But we want to unify them just to make things easier for us. So that's why we now made this pair. So anywhere we see x, y, we use x. Anywhere we see x, z, we use y. Anywhere we see y, z, we use z. So we now rewrote this formula as this. Makes sense up to this point, right? So after rewriting it as this, you can remember that we have already defined a to be k minus 2. So that's just what we did here. Anyway, we see a of x, so x minus 2. Okay. So a of x, x minus 2, a of y, y minus 2, and a of z, z minus 2. Makes sense, right? So we just did the multiplication. Expanded, and we got this polynomial. So what we're now trying to say is that this big polynomial here is equal to this polynomial here, which it should, right? Because it's just a multiplication. And so what we're now trying to say in essence is that if we evaluate this p polynomial, which is this big polynomial, at thanks. This thing. I don't know if it's this. I'm not sure it is. Okay. But we need it. Just. Okay, so if we evaluate this polynomial with these values, right, it should be the same thing as us evaluating this polynomial with okay, what was that? X, Y, Z. So we can substitute. So this is 48, right? Good. So what I'm trying to say is that we evaluated this and we got 48. If we also evaluate this polynomial, this one, with still the same values, we should get 48. If we don't get 48, then Ojoro D. Abi? So if we don't get 48, there's a problem somewhere.
Sorry, the two you use in expanding the polynomial, is it a given or you it's just for example?
The two,
Yes, you used in expanding the polynomial.
no, it's just normal polynomial multiplication.
No, I know, like, at first we were like,
Okay.
yeah, like, no. Yes, like,
Okay, this
like X
K
minus
minus
2,
2.
Y minus.
No, we just picked.
Okay.
Yeah, we just chose. We just chose an arbitrary polynomial. Does it make sense up to this point?
Yeah.
Sure.
My question is, why we are using x, y, z is because we are looking for a triangle, right? If we are
Yeah.
looking for a square, we use ABC.
Yeah, we'll use ABCD. If you're looking for an octagon, you use ABCD up to you get. But that is the idea. Are we okay up to this point? So we can see that even in this case, right, if we pass, let's say x was 4, right, y was 6, right, and z was 8. If we pass that in here, internally a will take what it wants. Like this first a is just going to take 4, this second a is just going to take 6, right, and this last a is just going to take 8, right, like based on this polynomial. That's basically this one here. Like everything just go where you are needed, go where you're needed, right? So everything makes sense up to this point, right? Dean, you're with us again, right? Okay. So now we've seen. So a in this case now, a is the polynomial that tells us if there is a connection between two people, and p is the polynomial that tells us if there is a triangle, right? Good. So to get all possible triangles in the network, all we need to do is find all possible combinations of people in the network that form a triangle. We check them. If there's no triangle between them, we get a 0. If there's a triangle, we get a 1. We go to the next set. We evaluate, and we keep accumulating, like 0 plus the accumulated sum is still 0. When we get a 1 plus the accumulated will be accumulated plus 1. We evaluate again, accumulated plus, let's say 0, accumulated plus 1, and we keep going like that. So by the time we've gone through all possible combinations of x, y, z, we'll have the total number of triangles in the network. Does that make sense? It makes sense, right? Please, if it doesn't make sense, ask. This is the problem statement. You get? So basically we understand this, right? So in essence, do we understand the problem statement?
Yes.
Are we sure we understand the
The
problem
problem
statement?
statement is how to like get the number of triangles, possible triangles
In the network.
in the network, and you say to do that we create like the running sum, right? So
Yeah.
from what I understood is that, let's say you have like a variable that holds the count, then when you do the running sum, the running sum is like you're evaluating each of three sub-polynomials. So when you multiply them together and they give you one, you add it to that variable that you've created. So if the next one you do is 0, you add 0, which still keeps the variable. So at the end of the day, the total count there gives you the total number of triangles.
Exactly. So everybody comfortable up to this point? I know I like asking that question. Are we okay? Are we together? Are we comfortable? Okay.
So, I noticed you're doing like a lot of arbitrary stuff. I don't know if that's like following some type of law or something, or it's just, I don't really get it. Like, first of all, you set x, y to a single value, and
Okay.
xz to a single value, yz to a single value, and then you create an arbitrary k minus 2.
No, that one is just an example, just to allow us to visualize like what we are saying. It's just an example.
Okay, so it doesn't help us know, it doesn't help us prove that there is also number of triangles in our graph.
This now, no, this doesn't have like we can't apply this directly to our problem statement. Okay, this one is just like an example I just brought out. Like you can think of this k minus 2. It's just a random polynomial I just came up with. Yeah. But you can think of it as that a polynomial. I was just trying to show why this p polynomial here should be equal to this a polynomial, no matter like it's not a must to be k minus 2. It may be any other thing, but in as much as we have defined this equality, the equality should hold no matter what this polynomial is. Like I'm just trying to like abstract it so that I just hope I didn't confuse you along the way. Are you sure, or you're just? Are you sure?
It's just like an example.
Yeah, just an example. Okay. Okay. So now we have our problem statements, and we'll be going into the Sumcheck protocol. Okay. So basically, when you hear Sumcheck, sum, right? Sum and check. So you're summing and you're checking. Right. So the Sumcheck protocol enables us to verify that the sum of the evaluations of a polynomial is a particular value without requiring us to do the computation ourselves. You can remember in our problem statement, our original, what the verifier wants is the total number of triangles in the network. But the verifier does not want to evaluate the polynomial at all those possible combinations. The verifier does not want to evaluate the polynomial at all those possible combinations. That's a lot of work for the verifier. So the verifier says, okay, take this work, he gives it to the prover, do it for me, evaluate this polynomial at all these possible combinations, then give me the final answer. But the verifier wants to be sure that final answer the prover gave is correct without doing that computation. Is it possible? Does it look possible? It does. Interesting. How?
Like, okay.
When the verifier picks a random point and maybe he knows the results, I'm sure, I guess he has some values to the parameters to be, I'm sure he has he has a trace now of the computation. Does he have access to the trace?
So the trace. In this situation,
Of some of them.
yeah. Let's just say yes.
Then you can check that, this particular point, a random point, if you check that parameter and you see that that's the result of that particular computation, in this case, polynomial. If you can check once or twice, how will be wrong?
Okay, good. That's true, right? So, can you relate that with the Apple scenario yesterday?
If the policeman checks the final.
No, not on the policeman side, on the verifier side.
Who's the verifier in that case?
Like you now, like after we've amplified the error, right? Let's just okay.
I think
I don't
there was a scenario she gave yesterday that already answered that question
about marking,
the
right?
apple. So,
Like you pick the apple
so
and
you
then
pick
not
that
the
one.
ones don't match that we don't.
Yeah, exactly. Then that should work. So okay. Yeah, I think that should work. Okay. So I think let's just continue and then we see. So we want to delegate that computation to a third party, right? To do that evaluation and some, let the guy handle it and give us the results. So let's look at an illustration of the Sumcheck protocol over a polynomial of 3 variables. Please pay attention. So this is an arbitrary polynomial, just a random polynomial that we'll be using for this example. But the main thing is it can be any polynomial, right? So we are using 2a plus 2bc as a polynomial. And we want to evaluate that polynomial over all possible combinations of 3 bits. Here we have 3 variables, a, b, c, right? And we want to evaluate and sum all the evaluations. So do we agree that these are all possible combinations of 3 variables, where each variable is a bit? We agree, right? So this is what the verifier wants. The verifier wants the sum of all these. like evaluate this polynomial at all these points and then give me the sum. That's what the verifier wants. So the prover then does it, right? The verifier gives the work to the prover does it. Substitutes this first one for A, second for B, and then C. After evaluating, the prover claims the sum is sorry. So after evaluating and summing, the prover claims that the sum is 12. Is the sum 12? It's 12, right? There's 2, 4, 6, 8, 12. So the prover claims the sum is 12. For the verifier, why will I believe it? You're telling me the sum is 12. Why will I believe it? You can just tell me the sum is 24, right? So the prover has to convince the verifier that the sum is actually 12. For the verifier to accept, the verifier needs the prover to evaluate the polynomial at random points chosen by the verifier. So it's just like the whole concept of the verifier dipping his hand to pick a random apple and check, right? So the verifier needs the prover to evaluate the polynomial at random points chosen by the verifier. So to do this, the prover needs to send a univariate polynomial of each in terms of each variable. In this case, we have like ABC, right, which is a multivariate polynomial, right? Well, the prover will need, like, by the end of the protocol, the prover must have sent a univariate polynomial with respect to each variable. We are going to talk about how the prover is going to generate those univariate polynomials based on the randomness chosen by the verifier. So it's based on the randomness chosen by the verifier that the prover is able to generate those univariate polynomials. Let's see how that is done. Okay, so firstly, at the beginning of the protocol, the prover is expected to send a univariate polynomial to the verifier. How does the prover get that univariate polynomial? If we can, okay, let's look at this. Do we notice any pattern in this sequence? Yeah. So we have 0, 0, 0, 0, and we have so we have like 0, 0, 0, 0. We have 1, 1, 1, 1. Right? So that basically means we can split this stuff into two. Right? The one where A is all zeros and the one where A is all ones. Does that make sense? And we can make A a variable, right? So that's just basically how it's going to be done. Let's just go forward. So this is it. We split it into two, where A is all zeros and where A is all zeros and where A is all ones. And then for B and C, we find all possible combinations of B and C.
So I'm lost already. Even in the slide before this.
Okay.
At that point we got 12. Like, how do we prove something?
Sorry, I'm coming. Let me. Sorry, which again?
Yeah, the slide where we got 12 there. Yeah.
Okay, this slide.
Yeah.
Okay. So remember, what the verifier wants is to evaluate the polynomial 2a plus 2bc at all possible combinations of a, b, and c. And from what we've seen earlier, like all possible combinations of a, b, and c means like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, up to 1, 1, 1, right? So the verifier wants to evaluate this polynomial at all these points and then sum the results. So it shifts that work to the prover. The prover does the work, evaluates this polynomial, and then sums the results to get 12. Is everybody like, is it clear for everybody
Yes.
up to this point? Are we sure? So now the prover got 12, but he now needs to prove to the verifier that he actually got 12 after evaluating and doing the summation. So that's
So from the start, we had the 2a plus 2bc way. We don't have like.
yeah, you have the verifier has the polynomial.
So we gave it to the prover
Yeah.
to run some computation and then got a particular value.
Yes.
So and the person wants to prove the prover wants to prove that they actually got that.
12. Yes. And the prover wants to prove to us that they actually did the computation and got 12. And us as a verifier, we want to believe the prover, but we don't want to do the work. We don't believe the prover, we don't trust him. Right? But we don't want to do the work. So we're trying to reduce the amount of work we are going to do. Right? We just want to do like something simple, but then we'll be, kind of be like 100% sure that the prover actually did those evaluation and summation
So by reducing the work that we do as verifiers, that means we're putting more work
on the prover. Yes. Yes. Does it make sense up to this point? It does, right? Okay. So in order for the verifier to be convinced, the verifier is going to pick some random values and send them to the prover, and the prover will be expected to work on those random values and return something back to the verifier. So we're going to talk about like the process, what is involved now.
So, in this scenario now,
Yeah.
which one of them is the trace?
The trace.
Yeah, is it the calculation that was done by the prover or the proof itself?
So in this case, we can. It's not in all situations that there is a trace per se. Yeah. It's not in all situations. But in this case, if you want, you can call this array the trace. Right? So you can call this array the trace. Does it make sense? Because this is like proof of work. Like if the prover is able to generate this array correctly, that means the prover actually did the work. Right? And then let's say the work will just be like summing it up. Does it make sense? Makes sense. Everybody. Okay, so like I said, like the verifier would select some random values, send them to the prover. The prover is going to do some work with those random values and send back to the verifier. It's like an interactive protocol. So the verifier, it sends the polynomial to the prover, evaluates and tell me the result. The prover evaluates and tells him the result. You can see there's an interaction. Then the verifier says, okay, I've seen the result, but I don't believe. Okay, do this. And the verifier says, okay, I've done what you want. Here is the result. And the verifier says, oh, I'm not still convinced. Do this extra work. And the prover says, okay, I've done that extra work. Here is the result. The verifier still says, no, I'm not still convinced. So so we're going to see like the whole interaction. Okay.
Okay, so is it more like a TCP connection, like a three-way handshake TCP connection?
Bro, you're going too far. You're going too far, bro.
You mentioned something. We are networking now about TCP connection, three-way handshake. So Ali send the message to you. So
sorry, but we are not even talking about network.
I'm trying to get, is it something like that? Is it like a three-way handshake?
I think where the three-way handshake comes in is where you check that it is a triangle. Because that's actually where the
according to what is saying,
like let's I know you're probably trying to abstract, I get, but I think that abstraction maybe like taking it to you can just something. It's just an interaction, like me and you were discussing. You can just think of it that way. No need of bringing in networking.
I'm trying to understand. Like you mentioned something about the prover sending something to the verifier, so they are interacting. One has to not confirm. So it's not like a two-way process. Like actually more than that.
No, that's what I'm saying. It's an interaction. So it's a two-way process, like you said. But I'm just trying to say like the whole networking aspect, bringing in the three-way communication. It's just a two-way communication.
It's a two-way, it's not a three-way communication.
Yeah.
Okay.
But it depends on how you want to think of it. But I don't want to go that way yet, so that we don't get confused.
So I don't know. Not to like go into what like we have not got into, but I just want to like get the picture clearer early enough. So based on this explanation, that this whole Sumcheck stuff, it shows that there's a back and forth interaction.
Yeah.
And going back to the difference between snap and stack, snap is non-interactive, right? So which means this whole Sumcheck is not applicable to snap because it's non-interactive. That's right.
No. But like you can build an interactive protocol,
Yeah.
right, and then make the interactive protocol non-interactive. We're going to talk about that. So that's where we start hearing things like fiat shamir. Yeah. No, not even the secret sharing. Fiat shamir is a process of turning an interactive protocol to a non-interactive protocol. Yeah. So we'll be talking about that soon. And you'll be building a fiat shamir transcript.
Me?
All of you. all of you will be building it. It's not difficult, so don't be afraid. It's not difficult. So we'll be talking about that. Like for now, we are talking of the interactive protocol, right? So normally, like snacks, we have succinct non-interactive argument of knowledge, right? One is the succinctness. The succinctness can be, let's not go there first. Okay. Let's just finish with this, then maybe we can just discuss and touch those other areas. Okay, so it's going to be an interactive protocol, but we can make it non-interactive. It's very easy to make it non-interactive, just as it's easy to make it zero knowledge. Right. So you can add non-interactivity, you can add zero knowledge, like after you have the whole soup.
So the main thing now is the argument of knowledge.
Yeah, the proof, the argument of knowledge.
Okay. This part now is the argument of knowledge.
Yeah. Or you can call it like, yeah. But normally, like when you see articles, they'll say a snack is made up of an IOP, which is like an interactive oracle proof, and then an interactive oracle proof, which is an IOP plus a polynomial commitment scheme.
Which is a succinct.
Yeah, which makes that proof succinct. Yeah. So like the protocol to like there are interactive oracle proofs. There are oracle proofs. There can be like different proof models, like different ways of generating proofs. And then but those proofs that are generated may be large. Then you use a polynomial commitment scheme to reduce the size to make it succinct. Okay, so what I was just driving at is that it's an interactive protocol. Do we all get that?
Yes.
So sir, you were still explaining the stuff that before his question, stuff that where the verifier needs to send randomly selected points for
Yeah.
the prover to evaluate at those points and send back. So I think that was it.
Yeah, I was just giving like a high level overview of the protocol so that we can now go like into it and see how it happens. Yeah. So basically for each round of the interaction, the verifier samples a random number or a random challenge and sends it to the prover to do some work with it. Then the prover sends a result. Then based on that result, the verifier can either accept or reject or still send another random challenge. Then the prover does work, send back the result. So that's the interaction. Are we okay, right? Rahim, are you with us? Are you sure? If you have any question, ask. Brethren. Okay, so we, like everybody agreed that there was a pattern in this, right? We have all zeros, all ones. We agree. So basically, after the prover sends the results, that 12 to the verifier says, I'm not convinced. Convince me. Right? The prover then needs to send a univariate polynomial. You know, this 2a plus 2bc is a multivariate. Multiple variables. It has multiple variables. The prover then needs to send a univariate polynomial to the verifier based on the initial polynomial. We're going to talk about how the prover is going to generate that univariate polynomial. So based on the fact that there is a pattern where we have like all zeros and all ones, right? That means anywhere we see A can either be a 0 or a 1, right? B can either be a 0 or a 1, C can either be a 0 or a 1. So we can take A as a variable like we've seen here, thereby reducing this, instead of it to now be 8 evaluations, we half the size. So this, I don't know if it makes sense. So we made A variable. When A is 0, we can get all these parts, right?
Yes.
It doesn't make sense. But you understand how we splitted this?
Zeros and ones.
Yeah, zeros and ones for A, just A, right? Which is like the first variable, right? So let's say we just forget about this guy and we make A here a variable, A. That will give us something like this.
Replace 0 with A.
Yeah, so if we replace A with 0, we are going to get all these values, which is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. If we replace A with a 1, we are going to get all these values, which is 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1.
Yes.
Does it make sense?
Yeah.
It does, right? So now, taking A as a variable and using all possible combinations of the remaining bits, which is like 0, 0, like once we make A a variable, like so we're working with like 2 variables now, right? And all possible combinations of 2 variables is 4, right? Which is 0, 0, 0, 1, 1, 0, 1, 1. Right? Do we all agree?
Yeah.
Sure? So where A can either be a 0 or a 1. So now the prover evaluates this polynomial or substitutes this value to this initial polynomial. So when we substitute, we get 2A. And as much as I say 0, this one zeroes out.
Makes it faster.
Right? So it zeroes it out, 0, 0. And then for this one, since it's 1, 1, that's 2A plus 2. Right? Which is this 2A plus 2 we got here. So the prover now adds all these polynomials together. We can see that after adding all these polynomials together, we get a univariate polynomial. A polynomial in just one variable, which is A.
Question.
Okay.
If I decide to use the B, will I get similar thing? Will I arrive at the same answer?
You arrive at a different answer, but well, it's a process. We're still going to do that. Yeah. So that is the whole essence. In the Sumcheck protocol, the number of rounds is basically the number of variables. So for each, does that make sense?
Yeah.
The number of rounds is equal to the number of variables. So for each round, we are generating a univariate polynomial in a certain variable. Does that make sense? So this is the first round now, and we are generating a univariate polynomial in the first variable, which is a.
Sorry. When you say the number of rounds, it's the number of like, how do you mean exactly? Because like, what's the round?
The round is the interaction.
Okay.
Yeah. So if there are three variables,
here now, yes.
that means there's going to be
Three rounds.
three interactions. Like I send something, you send back one. I send another thing, you send back two. I send another thing, you send back three.
So, do we have the round like depicted here? Or
Yes, yes, we are getting to it. Does it make sense up to this point? Sure? Are we sure?
Please, can you go back to the previous
Yes,
slide?
please.
Okay, where A can either be 1 or 0.
Yeah.
Okay,
So if A is 0, we are going to get back all this.
okay,
If A is 1, we are going to get back all this.
okay, so move to the next slide. Okay, so from that equation, 2A, so A00 is 2A.
So we just substitute A is still a variable.
Yes,
0, 0, that's B and C.
okay,
So that will give us 2A plus 2 times 0 times 0 is 0.
alright, makes sense.
2 times 0 times 1 is 0. That's why this one is still 2A.
Yeah.
Does it make sense? Does it make sense how we got 8A plus 2?
Yes.
We just add them together. Okay. So the prover sums the partial, what we call this is a partial evaluation. Right? We have evaluation of a polynomial where we give a concrete value to all the variables. So if we want to fully evaluate this polynomial, we need to put a value for A, B, and C. But since we are not putting a concrete value for all the variables, we are just putting a concrete value for B and C. That's a partial evaluation. Does that make sense? Okay. So the prover sums the partial evaluation and sends the univariate polynomial in terms of A to the verifier, which is 8A plus 2. The prover sends this 8A plus 2 to the verifier. Does that make sense?
So the prover is going to repeat this process 3 times. This
Yeah.
is the first one.
It is the
So
first
do the
one.
same thing for B and the same thing for C.
Yes. But this makes sense so far, right? So when the prover sends this polynomial to the verifier, all the verifier needs to do is now to evaluate this polynomial at 0 and 1 and then add it together. Does it make sense why it's 0 and 1? Why? So when we evaluate this 8A plus 2 at 0, we are meant to get the sum of all these ones. If we evaluate at 1, we are meant to get the sum of all these. And that's what the verifier does. Evaluates at 0, gets 2, evaluates at 1, gets 10. Okay. Sorry? Sorry, I'm coming. Just a minute. Okay. So my question, okay, first of all, do you understand how we got 8a plus 2?
Some of the partial results.
Yeah, this is some of the partial evaluation. Do you know why we did the partial evaluation?
So that because we verify question for it.
So that,
Because we verify question for it.
yeah. But do you know why how do I ask this?
So that can you go back? Can you go back? That same slide.
So the prover sends just this polynomial, this 8a plus 2.
So that
In the
is
first round.
The first round, together with that final calculation, the sum.
The sum, yeah. The program must have already sent that sum of 12. Yes.
So I thought the reason we are doing a partial evaluation is to simplify and reduce the number of variables that we're working with at a particular time.
Yeah, that's part of the reason. Yeah. That's part of the reasons.
so the initial logic for 2a plus 2b, breaking them down from 0, 0, 0 and all was just to get this 8a plus 2 for him to be able to give to the verifier to just verify at any point that his logic is correct.
Yes. Does it make sense?
Yes, there's no part you're talking about that you said that was like you added these two and then gave us the 12, right? There was one part that was showing
Which one? No, we've not gotten to that part.
I think that yes, that once you add them together, that's going to be 12. Yes, but
No, if we add them together here, it will give us 12. If you check, like, if we add all this together, it will give us 2. Right? 0 plus 0 plus 0 plus 2. Yeah. And this 2 plus 2 plus 2 plus 4. This will give us 10. So this is just what the verifier is trying to do on the verifier side now. By evaluating that 8a plus 2 at 0. Evaluating it at 0 will give the verifier this 1, 2.
8a plus 2, that would be 2.
That will be 2.
I want to understand the other.
Okay, no problem. Okay, no problem.
That's why
Okay, you can.
you're answering me. I want to answer because that's the option. That's all you.
Okay. But are you
Okay. We're talking about one value having 0 and another one having 1.
Is it explain to people, right? Pictures I've seen on social media. I want you guys to know that I'm doing
control for able to Gen Z.
It's actually the focus on control. See.
This for self-extension. To my
We'll be locking our door.
Goodness not trust my life with God. Not trust him to sue. And goodness will let. Goodness will hear me now. I don't say this.
Because on all the positive side, those are the ones that design the post.
No. So you see, do you watch the interview with Jarvis and Bella?
Yeah.
That's the way he was speaking English. Nobody was taking him seriously. And when he started speaking very broken English, that's when people now started. No, man, people are depressed. They only want content that makes them laugh. So we too, we are like, are you following? You see the way our numbers are growing.
I don't thank you.
This is our work pass, yo. You know why I say nobody from business school.
I said, no, Alex, I don't remember.
You know why business is most paid? Because business are finished spending this picture. So it's against him. Oh, thank God you can call us. Business went to wedding. Let's not take any picture. Not put anything. It was creating meme. This guy last week. So basically, yes. That's basically the meme. That's the fact. That's the meme contractor with 3 If 2A plus 2BC, that's when the zero. Back comes 0.32. I mean, guys should give me no complaint.
Okay. Okay, so
I wanted to ask something.
is it?
Yeah, I just want to say that if what
So I'm coming to your question.
what the verifier is going to do is just to evaluate that univariate polynomial and get to. That means the verifier must have calculated this polynomial to know that if it sums this part, it's going to get 2. And if it sums this part, it's going to get 10. Because how else does he know that at this point it is 2? And at this point it is...
We're going to get to that point. Just be patient. We'll get to that point. Sorry. Okay. Yeah.
So, like, the goal of like the verifier and prover stuff is just to like delegate heavy work to the prover and give like verifier little work to do. So the verifier is just evaluating univariate polynomials. So it's not heavy work. Like, so it is the prover that is evaluating the multivariate polynomials and giving back just univariate polynomials. Simple polynomials that the verifier can like evaluate.
Yeah.
Who is responding to me?
Yeah, to you. But it will get clearer when we get to the end of the protocol.
Okay.
Your question, I understand where you're going. By the time we get to the end of the protocol, it will make more sense. Okay, so that's true. You have that thing.
So that's the next leg. Why did we pick 1 and 0? The next one.
This
Yeah. Why not maybe 1 or 0?
No, it's because of this.
0.
Yeah, it's because of this. Yes. So we want to get back this. The verifier wants to get back these values.
Let us assume we split it into 3 parts. Maybe that was 2.
Yeah.
We do 0, 1, 2.
0, 1, 2, but that now is kind of like you can still build a Sumcheck protocol out of that, but I don't want us to get into it so that yes. Okay, so
Can you go through the second? Yeah, please. Just one more time. Please,
okay, I'll I think let me start from here so that I can answer question too. So let me start from here. So firstly, like, you know why we broke it into two parts, right? Why we have this part and why we have this part.
So I got to look at this calendar, so I think I get it now. So this is different combination. This one there is like A is in front of it.
Yeah.
So like
A is here, but A is
So
zero.
this first A that like 0, 0, 0, and the second section has 1, 1, 1.
Yeah.
So I get it now because I was using
Okay.
Thank you.
So this one makes sense now, right? And you can see that if we make a variable, then we can basically like scrap. If we make a variable, we can, I won't say scrap, but the concrete values we will now need are concrete values for B and C, which is like 2 bits, right? And all possible combination of 2 bits is 4, which is 0, 0, 0, 1, 1, 0, 1, 1, 4 values. So since A here is a variable, if we substitute A with 0, we are supposed to get this, right? For this first one, if we substitute A with 0, we are meant to get 0, 0, 0. We are meant to get 0, 0, 1. Meant to get 0, 1, 0 and 0, 1, 1. If we substitute A with 1, we'll get 1, 0, 0. Here we'll get 1, 0, 1. We get 1, 1, 0. And we get 1, 1, 1. Makes sense, right? So what the prover does is now the prover generates these intermediate polynomials, which are these, right? A is still a variable, right? You can remember that, like, you can remember what happens if we substitute this variable A here, right? If we substitute this variable A here, it gives us this part. If we substitute it 1 here, it gives us this part. And that's just a similar thing here. As we have 2A plus 0, if we put 0, if we put 0 for A here, we are going to get this guy, right? And if we put 1 for A here, we are going to get this guy. Does it make sense?
So basically, it's still the same polynomial, but the other values is A unknown.
Yes, with A as the unknown, exactly. Still the same polynomial, but with A as the unknown. Same thing for this one, right? If we put A as 0, that would be 0, 0, 1, right? Which is 0, 0, 1, which will give us 0. If we put A as 1, that would be 1, 0, 1, right? Which will give us 1, 0, 1, which will give us 2. Same thing for this and for this, right? But now we're talking about it with respect to the variables. But now let's think of it with respect to the polynomial. And that's what the prover does. The prover actually generates this polynomial. And that's how we get this 8a plus 2. So this 8a plus 2 is kind of like a summary of everything here. In a sense that if we substitute A here with 0, we are going to get the sum of all these values, where A is 0. Does it make sense? And still this 8a plus 2, if we substitute a with 1, we are going to get the sum of all these values where a is 1. Does that make sense?
So A becomes the major determinant.
Yes.
Check which side it falls.
Which side? And that's what the verifier does. The prover sends 8a plus 2 to the verifier. And that's what the verifier does. The verifier evaluates a at 8a plus 2 at 0 to get 2. And also evaluates 8a plus 2 at 1 to get 10. And sums it up to get 12. And then the verifier checks if the answer he got is equal to the answer the prover sent at the beginning of the protocol. If it's not equal, that means Ojoro, Abi. If it's not equal, then the verifier rejects.
So this is a complete flaw of Sumcheck.
No. What's the first round?
Yes. But the thing is, even if we do the second one and the third one, it will still
It's still the
give
same
us the
thing.
result.
Exactly. Similar, something similar. But we have not talked about randomness, how randomness comes in. So we need to talk about like how randomness plays a part in this protocol now.
So my question is, the verifier does not know A.
The verifier.
Yeah, because what the verifier gave the prover was the polynomial that was known to him. So he gave it to the prover, and the prover recorded an answer, which is what the result of the computation that the verifier was expecting. Right? It doesn't have to be correct or not, but the verifier knows that it's expecting a value. So that's which is the result of the computation. So now he doesn't believe, and he says, okay, prove me that this is it. Then the prover does some things to the polynomial and gives him back a invariant. But then the verifier is not aware of A. So how is the verifier?
No, it's a standard in the protocol. That's why we went with the Boolean representation of the labels.
So do you the verifier automatically know what A is?
The verifier, that univariate polynomial the prover sends, the verifier evaluates it at 0 and 1 and sums the result.
So no matter what the polynomial is, the protocol is to evaluate it at 0.
At 0 and 1. Yes. But do you know why we're actually evaluating it at 0 and 1?
Yeah, I think based off the substitution we made, like when we splitted them,
Splitted it, exactly.
It became 0 and 1. So
Exactly. That's the reason. Does it make sense? I know it can be confusing, true, right? But if at any point you miss something, please shout. Or shout. Please just shout.
So is it is it what we are focused on A being our major points of classification and stuff? Is there any equation that would maybe focus on something that is 2 bits, like maybe BC, rather than the focus being on the 1 bit, or is it always better to maybe focus on the 1 bit?
We focus on 1 bit, like the
for example,
univariate.
we started with 2A plus
2BC.
Now, in this sense now, A is 1 bit, BC is 2 bits. So it's easier to put focus on A and just have BC calculate down so that we can now use A as a point of reference to get the whole sum, just like we did here. Now my question now is, can there be a large enough equation where maybe the smallest we can have is maybe a kind of BC like maybe AB plus something BCD.
Okay,
Then
so just think of like B and C are 1 bit on their own. So don't think of BC as like as 2 bits per se. Good and fine is 2 bits, but don't. I think the way you're thinking about it right now is thinking that A is maybe because of the way the example we used. But I think like when we get to the second round of the protocol, maybe you'll get an answer to your question. Are we okay? Okay, so we can go to the next round, right?
Yeah.
But do you understand what happened here? After the verifier evaluated at 0 and 1 and summed the results, the verifier then checked if what he got is equal to what the prover said the result is. If it's the same, the verifier says okay. Yeah, okay, good and fine, okay, but I'm not still convinced. Right. But if it's not equal, the verifier says, oh, you are lying to me, that type of thing. You get. So in this case, they are equal, so the verifier says, okay, but I'm not still convinced. But why? Why would the verifier say so? We still got 12, right? But let's just think of something. In this scenario, it's possible that in the initial array, right, these 2 might have been here. Say if the prover lied. The prover might have lied that the evaluation at 000 was 2, right? And the evaluation at 011 was 0, right? But that sum will still give us 2, right? And also in this case, the evaluation, the prover might have lied, and then like the evaluation at 101 will be 4, but the evaluation at 111 will be 2. So it's mixed up, but the summation is still consistent, right? So that is why the verifier says, okay, I got 12, and what you said was the result was 12, but I'm not still convinced. Convince me further. So now we go to the next round of the protocol. The verifier is not fully convinced, so the verifier samples a random challenge and sends it to the prover. This is where randomness now comes in. The verifier samples 6. R1, let R1 be 6. Right? And sends it to the prover. So what does the prover do with this random challenge? Let's see. The prover partially evaluates the original polynomial at A equal to the random challenge. Does that make sense?
This is the previous slide again.
Eh?
The previous slide.
Okay. So we know that original polynomial 2a plus 2bc. The verifier sends the prover a random challenge r equal to 6 and tells the prover evaluate that original polynomial 2a plus 2bc at a equal to 6. At a equal to 6, which is the random challenge the verifier sends. Does that make sense?
Yeah.
So the prover does that, right? 2 evaluated like 2 times 6 plus 2bc, and the prover gets 12 plus 2bc. This is a new polynomial with lesser number of variables. right? Where A have been fixed to 6, right? So the prover now evaluates this new polynomial over the Boolean hypercube. This is the first time we are hearing Boolean hypercube. But I think I've talked about it. But the Boolean hypercube is just all possible combinations of, in this case, 2 bits. Because we have like 12 plus 2 BC. So BC is the variables we have here, which is like 2. So all possible combination of numbers that we can represent with 2 bits. Basically all what we've been doing since. Right. So the prover evaluates this polynomial now 12 plus 2 BC at all possible combinations of 2 bits.
So the R1 is simply pegging the A variable to 6.
Just pegging the A variable to 6.
Do you have any other variable?
Huh?
Do you have any other variable?
It's
random.
no, it's
I mean,
It's what the verifier gave back to you.
you don't understand. Like, do you have any
any other variable. No, it's actually a sequential.
Okay, so we're going to
In this case, in the Sumcheck case,
okay.
yeah,
That's the first variable.
yeah, because like the first round is kind of like for the first variable. If you want to think about it that way, it was
This
A.
is still one round.
So we're going into the second round now. We're going into the second round now, but like in the first round, it was the A variable that was evaluated as 0 and 1. So now we are now pegging that A variable to 6. Yes. No, it can be. That's why we say random. Yeah. Random.
So the 6 is random.
Yes.
What if the prover that beats 5?
It was the verifier that provided the 6 randomly.
So could it have been something, say 5?
It could have been 1 million.
Okay, so
But will
that
it
beats
evaluate
4
to,
So
Yeah.
but whatever it is, he said, will it still evaluate to 12?
That's part. We are going into the second round of the protocol now.
okay.
So the first round is we have A to the 0 and 1. Second round,
A 6.
randomness.
Like by the end of the first round, the verifier now sends the randomness, right? So we use that randomness to reduce the number of variables of the initial polynomial,
Okay.
right? So we have a new polynomial now where that first variable has been fixed.
Why did you use the first variable? Why not the second?
You're still in the first round.
That is because in the first round we split. You can remember where we defined A,
Yeah.
and like A can either be 0 or a 1.
Yeah.
So now we verify that okay, that's correct, right? So we now want to put a value for A that the prover cannot, that the prover cannot change. Like this, this now is going to affect what we are going to be working with till the end of the protocol.
Okay, so I say that a round is made up of like the splitting part and the randomness part. So for instance, the first round is we are dealing with A. And
The
so
splitting part, I'll call it like generation of the univariate polynomial.
then the second part is the randomness. And it's still with one round, that's when we are dealing with just A. So another round will move to B.
To B.
Would generate the univariate, send it, do the randomness again. The third round will now be for C. So every round is made up of generation of univariate and randomness.
Does it make sense?
Yeah.
Oh, makes sense. Nice. Okay, so so we can see now like that 6 can be anything, right? You can think of it as dipping your hand like error amplification, right? we can think of it as like error amplification. So we are not like that randomness now must not be 0 or 1. It can be 1 million, it can be it can be 2 billion. Okay, people that like money. So it can be like a trillion, it can be anything, but when you're calling those you'll be looking at the number of bits you're using to represent it. Right? So so now in this case we took randomness of 6. Right? Just so that for this example, the verifier sends a randomness of 6. The prover then evaluates that initial polynomial at a equal to 6 and gets a new polynomial which is 12 plus 2bc. Makes sense?
Yes.
So the prover then does the whole stuff again. Evaluates this 12 plus 2bc at all possible combinations of B and C to get these values, right? And then the prover sums it up and sends this answer 50 to the verifier. Can we see that this is kind of similar to the initial problem, but we have the size of evaluation.
We have 12 and it's 50.
No. Like in the initial one we had 3 like A, B, C. Yeah. So it was 8 evaluations we were summing. Right. But now we fixed the value for A. Right. Now we have just 2, which is B and C. So we have just 4 evaluations to do now. So the prover does these evaluations, sends this sum to the verifier, 50. Right. So the verifier is not still convinced with the 50. Right.
Can I say something? Okay, so if he was to be convinced with the 50, how can this 50 now convince him if he doesn't want to go further?
No, like with the 50 we need to go further.
Okay, with the 50 you need to go further.
We need to go further.
Why?
Because now it's just similar to why we started the protocol in the first place. Right? The prover is now telling you that okay, this new polynomial, the sum over the Boolean hypercube is 50. Just like what is said at the beginning of the protocol, that 2a plus 2bc, the sum over the Boolean hypercube is 12.
Mm-hmm.
But we did not believe, right? That's why we started the protocol.
So we are going further away, but not even coming closer to the 12 or something. Because the first one is 12, the second one now is 50.
No, the 12, forget about, we verified that one, we are done. We are done. Right?
You're passing new values to confirm the accuracy.
Yes. So we are done. So you don't need to compare 12 and 50. There's no relationship between them.
But I thought all evaluations should result to 12.
No. It's a new polynomial now because we fixed the value for A as 6.
Okay, so let me get something now. What is the prover trying to, or what is the verifier trying to verify? The polynomial. Is it the univariate polynomial that the verifier is trying to verify, or what? Or the values that you're getting from the sum of the Boolean hypercube, or blah, blah, blah.
The full protocol, right? What the verifier is trying to verify is that the sum over the Boolean hypercube is 12. Right? That is like what the verifier is trying to verify. So good and fine, you've given us the sum. That sum is what we are supposed to get. That is like the final answer. But we are now involving ourselves in this protocol where we are now breaking that big problem down into smaller problems that may have a different solution. But that 12, like at the end of the protocol, if the verifier accepts, then the verifier accepts that 12, that initial 12 was correct.
Okay, so as we go further, we will get to a point where we can then accept that
Yes, that initial 12 was correct.
Let's proceed.
Okay, but this 50 here, do you understand how we got 50? Does it make sense? So now the prover, this is the new polynomial now, 12 plus 2bc, right? A polynomial gotten by fixing a equal to 6 for the initial polynomial we started with. Is it getting confusing?
No.
Okay. So now after the verifier picked the value of 6 and the prover evaluated and got this polynomial 12 plus 2bc, the prover now needs to evaluate this 12 plus 2bc over the Boolean hypercube, which is what he did and got 50. And he now tells the verifier, okay, 50 is what I got by evaluating or by summing this new polynomial over the Boolean hypercube. But the verifier says, okay, 50, right? But I'm not convinced. You got 50 by evaluating this new polynomial over the Boolean hypercube, but I'm not convinced. Convince me. Right? Does it make sense? So for the prover to convince the verifier again, the prover needs to generate another univariate polynomial
From this particular one.
from this one. From this new polynomial now, the prover needs to generate another.
So the 12 we got at the other side.
We have verified that 12 by
Okay,
checking.
that's a totally different polynomial from this one.
Yeah, it's a different polynomial, but they are linked. They are linked. We are going to see how they are linked when the verifier wants to. That's what they call the verifier oracle check. That is at the end of the protocol. We are going to see why all these polynomials and how they are linked. Does it make sense? Okay. So now we have this new polynomial, right? 12 plus 2bc. The prover evaluates and sums it over the Boolean hypercube and gets 50. The verifier is not convinced. The verifier says, convince me. The prover is now meant to generate a univariate polynomial with respect to this polynomial. And can we see another thing in this sequence? We can see that same pattern, right? Yeah, 0, 0, 1, 1. That same pattern. That's what the prover just does. So a univariate polynomial in terms of B that the verifier can use to check. Yeah, so we split it again. It's making sense, right?
Yeah.
Good. You'll be implementing it too. Like, you're going to be implement this protocol with Rust. You can think of it that way. Yeah, you are going to be implementing this with Rust. This is Sumcheck protocol. If you check the syllables, you'll see Sumcheck protocol. So that's Sumcheck protocol in the syllables. That's what we're doing here. right?
We have started the syllabus.
But I'm not started.
Eh?
But just reviewing the workshop that was done in the Web3 Lagos and Technical Conference.
We are this. We are like this.
So, no, I'm not started.
We are the
No, I'm not started.
workshop. We are like.
When we start is when we start, like polynomial implementation is where we're actually meant to start. Polynomial implementation is where we're actually meant to start. But after this, I expect like the Sumcheck protocol, when we get to the Sumcheck protocol, where we are meant to do the Sumcheck protocol, I expect the Sumcheck protocol to be like a walkover for all of us. So the only thing will be like implementation details. Yeah, we rust. So, does it make sense? We can continue, right?
Yes.
So we see that this is 12 plus 2 BC, right? But we can think of 12 plus 2 BC as 2 times 6 plus 2 BC. We can still think of it that way, right? But what the prover is actually working with currently is 12 plus 2 BC. But we agree that these two polynomials are the same, right? 12 plus 2 BC and 2 times 6 plus 2 BC. We agree that they are the same, right? So the prover does the same thing, splits based on B now, right? And we make B a variable, meaning that when B is 0, we get this 2, right? And when B is 1, we get this 2, right? So the prover needs to now generate the univariate polynomial that he will send to the verifier, which is this.
Can I go back to the previous slide, please?
So if B is 0, this becomes 0, right? Meaning we have just 12.
Just like what we did with
Yeah, just like what we did with it.
Yeah, if we are only taking in the factors from B, why are we still expressing 0, 0, 0, 1? Why not just
No, we're just showing it now. Just like what we did here.
Yeah.
You get, it's just for us to see like visually what is going on. You get. So this is it now, right? Sorry, this should be C. Okay, yeah. So the prover needs to generate these two polynomials, right? We make B a variable and then put a value for C, right? And C can either be a 0 or a 1. Since it's just one bit. Make sense? So it's 12 plus 2 BC, right? When C is a 0, this becomes 0, right? So we have 12 here. Does that make sense? When C is a 1, we have 12 plus 2B. B is the variable. C is the value that we are putting, like constant value. Does it make sense?
Yes.
Huh?
Yes, sir.
Are we sure?
So at the end of the day, everything we now check at the point of 0 and 1 to equal to that 50 back.
Yeah, that is the verifier. So let's just go. So the prover now sums these two polynomials to get a univariate polynomial in terms of b, right? Which is 24 plus 2bc. Sorry, 24 plus 2b, right? And the prover, can we reduce? Yes, reduce this one, yeah. I know but it's necessary. Okay, so the univariate polynomial now is 24 plus 2b, right? The prover sends it to the verifier, right? I remember the verifier evaluates it at 0 and 1. When the verifier evaluates it at 0, the verifier is meant to get 24, which is the sum of these two. And when the verifier evaluates it at 1, the verifier is meant to get 26, which is this one, right? And then summing them together will give us 15, right? That univariate polynomial evaluated at 0 plus the univariate polynomial evaluated at 1 will give us 15. So after the verifier gets 50, the verifier then checks, is 50 equal to what the prover said the sum over the Boolean hypercube of this, of 12 plus 2bc is. And if we check, is it? It is, right? 50.
This concrete user sends the 50. This was before sending the univariate for me.
Yeah.
So at this point where the provider just sends this to verifier and then doesn't expect any response.
Yeah. When the prover sends this to the verifier, the prover is also meant to like the prover is now meant to also send the univariate polynomial. So it makes sense up to this point. Okay, so the verifier then checks 50. Okay, I evaluated at 0, got 24. Evaluated at 1, got 26. I added them up, I got 50. And 50 is equal to what the prover said the evaluation of 12 plus 2bc over the Boolean hypercube is. So the verifier says, okay, it's correct, right? But I'm not still convinced. So in this case, 12, so if you swap it, it may not be a problem, right? But in this case, 14, the prover might have gotten 14 when evaluating this polynomial at 1 and 0, right? So there's still that possibility of doing that swap. So that's why the verifier now they go for another round. Do we understand up to this point? Okay, so
Sorry, all this back and forth is within seconds.
yeah, within seconds. So for now, it's like an interaction, right? You can think of it as, if you want to think of it maybe in the blockchain setting, that's where you now start, where the whole networking thing comes into play, right? But for now, let's just think about it as like a normal interaction between two people, right? Then we're still also going to talk about like how to now render it non-interactive using fiat chimera so that you're not bothered about the whole network stuff. So okay. So the verifier is not still convinced, right? So the verifier sends another random point, which is R2 equal to 10. This R2 now is meant to replace B, right? R2 is meant to replace B. If we think of it, this is the new polynomial the prover is working with, 12 plus 2BC, right? And it's still equal to 2 times 6 plus 2BC, right? So if we substitute B to be equal to 10, that will give us 12 plus 20C.
What is the essence of the 2 into bracket 6? Why are you...
No, I'm still trying to make us to see how they are linked. That's what is here, like just for us to be able to see how that initial polynomial is linked to this polynomial now. And this is the way it's linked. Like 12 plus 20C, we can still think of it as 2 times 6 plus 2 times 10 times C. Does that make sense?
Yeah.
Makes sense, right?
Sorry, please. This R2,
Yeah.
the verifier is the one that provided it, right?
Yes, the
If you
verifier.
change that value from 10 to 11, does it not?
From 10 to 11.
Yeah.
If the verifier sends 11,
Okay, it's still balanced. on both
yeah,
sides.
it will still balance. Please, is it clear? Are we together? Any questions so far?
So if we have up to like 5 or 6 variables, we are going to go through this round 5 or 6 times
For all the variables.
for all the variables.
Okay.
I remember you said that the proof element is the proof of the computation that confirm as well, right? So now, the proof is the sum, right? Or the proof is the computation that you're trying to prove has been done. Is it the computation of the sum or the computation from that allowed us to get the polynomial in the first place?
Oh, the computation we're trying to prove is the sum of that initial polynomial over the Boolean hypercube. Over the Boolean hypercube, which is that initial 12 that the prover said that initial polynomial, which is 2a plus 2bc, evaluated over the Boolean hypercube, will give us 12. So that's what we're trying to prove, right? So the proof is an object. We can think of the proof as an object, right, that contains all these like the univariate polynomial and the claimed sum. I don't know if it makes sense. So that's the proof, because that's what the verifier now needs. Because the verifier takes the proof and either accepts or rejects. So when the verifier collects that proof, which is that object that contains the univariate polynomials, the multivariate polynomial is, yeah, that's what we're trying to prove. So the verifier already knows it. Yeah.
What is the Boolean hypercube?
All possible combinations of a particular number of bits. We're going to like when we get to that point, we are going to visualize the whole Boolean hypercube thing and why it even works.
There's no possible combination.
I'm not giving you a textbook definition.
Yeah, I know, right? I just want
You
to
get, but like all possible combination of binary numbers that can be represented with a certain bit, can be n bits. Yeah.
And I would take it.
So we're almost done.
Remain 12.
Okay, I think we can take like a 30 minutes break.
Are we finishing the slide today?
Yeah, we're finishing this slide. 30 is too much, right?
It's not too, it's perfect.
No, or let's continue. Like when it's time for lunch, then we take a break and
Let's just continue.
Please, you know, while you were scrolling, I saw the Fiat Shana. We are doing it today, right?
the Fiat Shamar, like, we're going to take it as a black box.
Okay.
Yeah, but I'll explain like how it can be used.
So, asking because it seems we're using this slide today, so Fiat Shana is there. That's what I'm asking.
Shama, it's not complicated per se. So when we talk about it, you'll see that it's just as easy as hashing something. Fiat Shama is just like using a hash function to basically generate randomness. So that's what it is like on a high level, using a hash function to generate randomness.
So kind of like really understand this, what's the like let's say cheat sheet to understanding things like how do you get to master it, or how did you get to master it?
Repetition, definitely. Repetition and like one thing is when you're able to draw connection between things, it's easier for you to link different things up. And when you link things up, like it's a kind of clarity you get. Maybe some things you didn't know were related, and let's say maybe you find a way to link them. It makes that thing stick, kind of. So I'll just feel like repetition and let's say reading research. But it's only by like reading and doing some research that you'll be able to like see some of those connections. So should we take the break? Should we continue? Let's finish this one, right? I think let's just finish this one and like get to. It's just one variable that is remaining now. Yeah, so let's just finish. Okay, so do we agree that these two things are the same?
Yeah.
We agree. Okay. So the prover evaluates this polynomial over the Boolean hypercube and sends the sum to the verifier. That is this 12 plus 20c. The Boolean hypercube in this case now is what? 12 plus 20c.
So for each round, it's different.
Yeah, it's a different Boolean hypercube because we are dealing with a lesser number of variables.
Okay, I'm trying to remember something. It's like when you differentiate something, then you derive, then later you differentiate, then you derive. So it seems like that's the progression.
Yeah, bro. Yeah, you can think of it that way.
The boolean hypercube is true.
What are the two this thing?
0 and 1.
0 and 1. Right. True. So evaluating at 0 gives 12. Evaluating at 1 gives 32. Right? So the prover sends this new sum to the verifier, 44. We can see that okay, the prover sends 44 to the verifier. We verified 50, right? 50 was correct. So now we're now at 44. So the verifier is not still convinced, right? So the prover needs to send a proof, which is a univariate polynomial in terms of C that the verifier can use to check. But yeah, it's already univariate, right?
Yeah.
So there is basically no need for the prover to. That univariate polynomial is basically what, yeah, it is. You get. So the verifier does not need to. The prover does not need to send a univariate polynomial again, right? Because this is already a univariate polynomial with respect to C. Yeah. So what the verifier does is that the verifier evaluates this univariate polynomial at 0 and 1.
You said the prover doesn't need to send a univariate polynomial. I think it should be the prover doesn't need to do the splitting.
The splitting. Yeah, but the prover sends like the sum over the Boolean hypercube.
Yeah, and then sends
which is 44.
the univariate that he used in getting that value.
Yeah. Does that make sense?
But what would the verifier be verifying, be comparing this result against for this particular?
That 44 now that the prover sent, which is like the meant to be the sum over the Boolean hypercube.
Yeah.
Which is, in this case, the Boolean hypercube is 0 and 1.
Yes.
The verifier is, the prover sends 44,
Yes.
right? And the polynomial, which is 12 plus 20c.
Yes.
What the verifier now needs to do is evaluate 12 plus 20c as 0 and 1.
So meaning that those initial time when he was sending the summation of all those things, it was not necessary if the verifier can just evaluate them at 0 and 1 and still get the same answer.
That's because those ones had multiple variables. They had some extra other variables. I don't know if it makes sense.
Sorry, probably what you are trying to do is that, like, giving a multivariate polynomial, so the prover will just break it down into a univariate, then send it to the verifier, then the verifier will not decide this value to confirm, right?
Yeah.
That's what you are doing, right?
Yes. So when we get to like one variable, that means we're already at the univariate, right? And the prover sends the evaluation of that univariate polynomial over the Boolean hypercube, which is the evaluation at 0 and 1, sends it to the verifier. And since it's a univariate polynomial, the prover does not need to generate another univariate polynomial, right? Then the verifier can just evaluate that polynomial as 0 and 1 and check if it's equal to what the prover said is meant to be equal to. And in this case, it will, right? Because when the verifier evaluates at 0, it gets 12. Evaluates at 1, it gets 32. So the verifier just accepts. Like once the verifier does the summation, gets 44, the verifier checks, is it equal to what the prover said? If it's equal, the verifier then, verifier accepts.
No good choice.
Okay. But C, we have not selected a random value for C. So normally what would have happened was that the verifier would generate a random number and send it to the prover, right? So that the prover will evaluate that polynomial at that random number, or partially evaluate that polynomial at that random number. But in this case, since there's just one variable C, after the verifier generates the random number, there's no need for the verifier to send that last random number to the prover, right? Because there's just one variable remaining, which is C. If we remember the other steps where there are multiple variables remaining, the verifier will send the random number, the prover will partially evaluate at that random number, and then sum the new polynomial over the Boolean hypercube, right? But in this case, since there's just one variable, there's no need to send the random number to the prover, because if we send the random number to the prover will return not a polynomial again, but an evaluation of the entire polynomial. But that's something the verifier can do by the verifier self.
So for every random number that is sent by the verifier, even if we are trying to do another check and stuff like that, the initial random number is still kept in that equation to go into the next round, and you keep the next random number. When we had A was 6, we still kept that value of A 6 even when we were checking B at 10 and stuff like that.
Yeah, that is why I was keeping this, to show that this 12 plus 20C is still the same thing as this. So we may be 12 plus 20C, but this 6 is still there, and this 10 is still there. Does it make sense?
Yeah.
It makes sense, right?
Those variables, like the 6 and the 10, those are the evidence that connects it to all the other.
So the previous ones.
Polynomial that we have been building from down to this one.
Yes. That's the evidence. So now it's now time for, after the verifier generates the last randomness, it's now time for the verifier to do an oracle check, right? Because the verifier is not sending this one to the prover again, right? The prover have already sent 12 plus 20C to the verifier, right? So what the verifier now does is that the verifier checks if 12 plus 20C evaluated at C equal to 8 is equal to 2A plus 2BC, which is the initial polynomial, evaluated at A equal to 6, B equal to 10, and C equal to 8. Does that make sense?
Yeah. I'm kind of on the last slide. Yeah. So I think what you said here, I just wanted to get to right. There's no point in sending the prover at this value, because once the prover, there's only one variable left, which is just synonymous to substituting the value
Directly, yes. So basically, this is like the oracle check the verifier does. that is that one check that the verifier wants to do. Instead of evaluating all the points over the Boolean hypercube, the verifier wants to evaluate the polynomial at just one random point. And that one random point is the, like call it coordinates now, where a equal to 6, b equal to 10, and c equal to 8. So this is the verifier's oracle check. And the verifier then checks if this value he gets when he does the oracle check is equal to evaluating this univariate polynomial at c equal to 8. If it's not equal, then there was, I call it Ojoro or Mago now. Right? If it's not equal, that means there was foul play like in the protocol. And this oracle check is what now gives the verifier that confidence that, oh yes, the evaluation or the sum of the initial polynomial 2a plus 2bc over the Boolean hypercube is equal to 12. Okay, I remember the 12 I'm talking about now, right? Yeah. That initial 12. Does it make sense? Questions. Let's take questions. Questions? Any question? Okay. So if no question, so since they are equal, the verifier accepts. The verifier just had to do a few tasks, which is like the evaluation of the univariate polynomial as 0 and 1, which is kind of like we can't really call that. That's not really a big deal, right? The big deal there is that oracle check for the verifier, evaluating the polynomial, the initial polynomial at one random point. So those other ones are just like minor checks the verifier just does to ensure that the protocol is consistent. So the verifier just had to do a few tasks to verify that the prover actually summed the evaluation of 2a plus 2bc over the Boolean hypercube.
Is it possible for the correct the back and forth, they are correct, and then the protocol
fails. That the prover is honest, but the protocol fails. Is it what you're trying to say?
Like
the check,
like all of
checks
the
in between checks out, but then the oracle check fails. I don't think it's possible.
It's possible. It's possible.
How? Why?
Let's not go into that for now. But it's possible. It's actually possible. Because okay, let me just give a hint. And that hint is that the prover can generate a random univariate polynomial for the rounds, right? The prover can generate a polynomial that just fits what the prover wants for those intermediate rounds, but the prover will not be able to. That will not save the prover from the verifier's oracle check. So that's kind of like when we like part of the security implications of the protocol. That's also like part of the security implications of the protocol, and also why the prover must not know the random challenge that the verifier would send. Because if the prover knows the random challenge that the verifier will send, the prover can just generate an arbitrary univariate polynomial that will fit and satisfy the intermediate round checks. So that's where, like, for those that will be looking into like ZK security, those are like things like that you will now like be try to take note of. Or we talk about like maybe soundness bug or something like that. Are we okay?
Yes.
Okay, so let's just like enumerate what the verifier did. So the verifier evaluated the f of a polynomial as 0 and 1, evaluated f of b as 0 and 1, evaluated f of c at 0 and 1. But then the verifier's main work was evaluating f of abc at abc.
Sorry,
Right?
Since the oracle check is done and like the answer is the same, so why the extra checks? Why the extra checks?
Which are the extra checks?
This one that you are doing.
No, this enumeration. We are done with the protocol. Though. This is summary.
Okay, this is summary.
We are done with Sumcheck.
We are done with Sumcheck.
Okay.
That oracle check is the final check of Sumcheck. That is the Sumcheck final check.
What the prover did and what
Yeah, what the verifier did.
Anything that we just did is some check.
Starting from the Sumcheck, like yesterday what we did yesterday was like just introduction to like error amplification and then like the problem statement, defining the problem statement and all. So what we just finished now is like Sumcheck protocol.
Do you use error amplifications anyway?
Error amplification is, in this case, is the verifier. The verifier evaluated at 6, 10, and 8. Those random points. But the initial polynomial we started with were just evaluations at binary values, right? But then the verifier was now able to evaluate at these random points, even if they were not part of the initial like polynomial we started with. But then like based on this random check, the verifier was now convinced that the prover actually did what the prover said he would do.
Sorry, let me ask, did you assume that there was error amplification? Did you assume that all
The polynomial gives us error amplification.
Okay.
Working with polynomials gives us error amplification. Yeah.
Okay, that's what I wanted because when you say that we checking at like passing those random values error amplification, I think that's the randomness.
Yeah, that's the randomness.
So does it handle the downsides too?
The downsides,
Yeah, like yesterday mentioned something like that.
the size.
Yeah, size. Does it handle cases like that?
Okay, so
Sorry, sir. Those points, are they like stuck?
which points?
Like that random point, 6, 10.
Those are that is the random.
That's random.
Yeah. That's like where the randomness comes in. Remember, like the verifier will still need to dip his hand from like after amplifying the errors, the verifier is going to dip his hand to So for the error amplification side of things, let's say with respect to that our networking problem now, right? Oh, no, not that networking. But the yes, the graph.
Oh, the graph.
Yes, the graph. So we had we had that array of yeah, you know, we had this array of values, right, that we interpolated to get the p polynomial, right? So if even if it's one of these values is not correct, let's say this 0,0,0,0,0,1 is meant to be a 1, but we have a 0, it will give us a totally different graph or a totally different curve. Right? It will give us a totally different curve. And if we now try to pick randomly, it will give us like a whole different, like, that's kind of like us encoding a different computation. That's kind of like encoding like a different computation entirely. So let me just run through like the enumeration like we've seen here. Evaluating at ABC. That's like the final oracle check the verifier does, right? That is the major work the verifier does. And for the prover needs to evaluate over the Boolean hypercube. Like for this first one, the prover had to evaluate over the Boolean hypercube. For the second polynomial, the prover had to evaluate over the Boolean hypercube. The third one too, the prover had to evaluate over the Boolean hypercube. So the prover is basically doing more work, right? Normally, the only work the prover should have done is like this first one, right? Which is actually what the verifier wants. It's a result of this first one that the verifier actually wants, which gave us that 12, right? But because the verifier wants to do a lesser amount of work, which is just checking one random point, that one now prompts the whole interaction, and what prompts the prover to do these other evaluations over the Boolean hypercube. So the prover does more work for the verifier to do a lesser amount of work. Does that make sense?
Yeah.
Okay. So in summary, the prover had to do more work for the verifier to do less work. Okay, but wait, like the protocol was interactive, meaning that both the prover and the verifier had to be available for the protocol to work. Right? For an interactive protocol, like two of us have to be here. If you're not here, I cannot be speaking to like the air, right? Can we do better now? Can we remove the need for interaction? Wait, but like, does the Sumcheck protocol make sense?
Yeah, it does.
It makes sense, right? So, can we do better now? Can we remove the need for an interaction? And that's where fiat chimera comes in. Right? So, with fiat chimera, we can remove the need for interaction. We can rely on the randomness and deterministic nature of hash functions. Mitch, please, what is the hash of, what is the SHA-256 hash of 502149?
So what is it?
SHA-256 hash of 502149. You can't guess it, right? You have to do it to know it. Right?
There's no way you can guess it.
So,
how many possibilities is there for you to get it?
yeah, so that's like the idea of fiat chimera.
So what to discuss it, we stop and take
And the randomness too also plays a part, because when the verifier sends a random shot, okay, let me not rush things. So whenever the prover sends a message to the verifier, the prover can hash that message, right? And when the prover receives a message from the verifier, the prover can sample it from a hash. We can think of it like as a hash function accumulator, right? We can think of it.
So meaning, what we are only just doing is just we are removing that immediate interaction. We are just having a kind of like encrypted conversation.
Exactly, encrypted conversation.
Like there should not be a like call and response immediately. They are still going to be sending the information to themselves, but I mean it's going to be in a kind of like encrypted manner or something like that they can respond at any time.
Oh, they are responding immediately. The idea is to be able to okay, let's just look at it this way. We have a transcript, a HTML transcript, and that transcript, you can think of it as like an accumulator, like a hash function accumulator. In the Sumcheck protocol, we saw the interactions that took place, right? But in this case now, when we try to remove interaction, we remove the verifier and the transcript stands in place of the verifier. So anytime the prover wants to send a message to the verifier, the prover appends that message to the transcript. Right? And whenever the prover is expecting a message from the verifier, the prover samples a random number from the transcript. So it's just like whenever the prover sends a message to the verifier, it's say let's say jumbles up what say what has been accumulated already, right? So that when the prover now samples a message, a challenge, it will be a different, like something totally random. I don't know if it makes sense.
So is the verifier responding?
The transcript is acting as a verifier. If you send a message to the transcript, because like the prover will need to send the univariate polynomial, right, to the verifier. But instead of sending it to the verifier now, the prover appends the univariate polynomial to the transcript.
So is the transcript reading it?
The transcript will take the message,
yes,
and use it as randomness for the hash. Like you can think of the transcript as a hash function, right? Where you have an input, you pass in the input, and it generates a hash of that input.
Yes.
So that hash now, you can think of that hash as the random challenge that the verifier sends back.
So is the transcript that's sending it back? Or
the prover is sampling it from the transcript.
Once the prover sends it to that transcript, the transcript does that hashing and stuff, and then the prover will just sample that result.
The hash, which is the output.
Oh, so it's not interacting with someone, it's just interacting with that transcript.
Just with the transcript.
So how do we enter transcript?
Huh?
How did we enter transcript?
Because we're not fiat
Oh, yeah, we are talking about like fiat chimera, right? We are trying to remove the interaction between the prover and the verifier. Yeah, if in an interactive protocol, the prover and the verifier need to be available, right? But the verifier is sending a random challenge, right? That's what the verifier is sending back to the prover when the verifier wants like when the verifier wants to send a random challenge. It's random. Right? And we cannot agree that hash functions generate random outputs. Do we agree?
Yeah.
It's deterministic, but it's random. Right?
Yeah.
It's deterministic, but it's random. So we are relying on that fact that hash functions are deterministic and random, right? In order to remove the need for interaction. So normally the way it would have been, the prover will send the message, let's say the univariate polynomial to the verifier, and the verifier will just pick one random number. Right? But now we are using a hash function to generate that random number.
And the randomness is based on the value the prover is sending.
The message the prover
based on the random number the verifier is sending.
No, we are taking away the verifier now.
Okay, we are taking away the verifier.
Yes.
Okay.
So that, like, okay, let me.
So that means when the prover sends his message to the transcript, like appends the message to the transcript has
uses the
this
message
As
with
randomness,
a random
as
a
an
random
input.
number, and then hash it. Then the prover will pick up that
For example, yes.
we check it out, we get that random number that the transcript used. Is that the random number is not going to use for his next verification?
For the next
Verification. So
Yeah.
it does his work again, appends it to the transcript, we hash it with another random number. Then they generate an hash. The prover gets that hash again and gets that random number again, and then go the third one.
The hash, you can think of the hash as basically the random number. A hash is a number, right?
Yeah. He used that hash as a random number.
So, sir, if I may understand what you're saying.
But the hash may be, so it depends on like how you go about the implementation, right? A hash, maybe if you're using let's say SHA-256.
No, he
That
said
means-
the transcript is going to generate a random number to hash the message that's coming from the prover.
From the prover.
So, like, what I was asking is that random number that the transcript using the random number the prover is trying to get, or the hashing after mixing that random number and the message from the prover to create that
Okay.
hash.
I think let me just draw like an illustration. We have a prover. We have a verifier. Right?
Yeah.
We have a prover and a verifier. The verifier tells the prover, evaluate this polynomial and give me the results. Like sum this polynomial over the Boolean hypercube and give me the result. Right? The prover sends that result. Okay. So the verifier sends the polynomial to the prover.
Sorry, please, can you make the verifier as paper so that we know it's transcript? Because this one is
No, I'm going to put the transcript. I want us to let's just visualize the interaction, right? Then I'm going to put the transcripts, say maybe here, which cuts off this guy. So the prover will just be interacting with the transcript. as opposed to interacting with the verifier.
Yeah, Shamil.
Okay, so the verifier sends the initial polynomial, right? The prover sends the sum of that polynomial over the Boolean hypercube and the univariate polynomial, right? And then the verifier samples a random challenge, like after evaluating the univariate polynomial as 0 and 1 and accepting, the verifier sends a random challenge to the prover. The prover substitutes that random challenge in the original polynomial to get a new polynomial, right? And then sends the sum of that new polynomial over the Boolean hypercube and also a univariate polynomial in terms of say the next variable b, right? And then they repeat the same thing. Let us say 3 rounds of interaction. This makes sense, right? This is basically what we've done. So now we are trying to, if this guy is not around, that means when the prover sends this message, this protocol will pause here and wait for when the verifier comes back so that the verifier can send the random challenge, right? And if the verifier sends the random challenge and at that time the prover goes somewhere, the verifier will have to wait, right? So now we're trying to remove that interaction by introducing a transcript. Right? So this transcript, you can think of it as a hash function, right? You can, like, at a high level, you can think of it as a hash function. Good and fine. The protocol starts with the verifier sending the initial polynomial, right? The protocol starts normally with the verifier sending the initial polynomial that he wants the prover.
The verifier sending.
Yes. Because you don't expect a transcript to initiate. Exactly. Does it make sense?
Yeah. But then is it also possible to replace the prover with the transcript as well?
But the prover needs to do work.
Yeah, like to be an automated process.
Oh, definitely. Like, it depends on the system, but all these things are automated, right? We're just talking about it like just for us to get, to be able to visualize it, right? But all these things are like this prover is, you can think of the prover as, let's say, the Starknet blockchain. You can think of the prover as Scroll blockchain. Then you can think of the verifier as Ethereum, right? Like if you want to think about it in the L1, L2 paradigm, right? So those ones, they want to prove that people perform transactions on them to the L1, right? So they are the prover, and the L1, which is Ethereum, is the verifier, where the verifier smart contract is, right? But let's not push it towards that side for now. We're still going to get there, right? So we introduce the transcript. So when the prover sends the claimed sum and the univariate polynomial, the prover sends it to the transcript. those of us who know how transcripts, how hash functions work, like depending on the hash function, there are some hash functions that absorb and squeeze, right? You can send it many values, it absorbs those values, and then when it wants to generate a hash, it squeezes. You can like sponge construction of a hash function, right? So it absorbs. So the transcript absorbs the claimed sum and the univariate polynomial, right? And the verifier now needs to send a random challenge to the prover. We cannot think of that as the squeezing phase, where we squeeze to generate the hash. And probably like based on that hash, we can now use that hash to generate like randomness that with that hash now we can say we can hash to a field, right? In order to get like a prime number that the prover can now work with as the randomness. So basically these transcripts now acts as a verifier to generate that random number and sends it back to the prover. So the prover is not waiting for the verifier himself. The prover is able to just sample that randomness from the transcript.
So how does the verifier know the random number that's
So the 2 point of authenticity in the whole interaction now is to ensure that the hash mechanism and the random number remains unique to the transcript such that no one has an idea of what it is, so that the prover does not kind of like know what is coming from the other side.
The hash function that for the transcript would have already been would have already been known.
Oh, the hash function is known by the prover also.
It's actually meant to be random, right? It's actually meant to be random.
Because I'm looking at the fact that since it is a transcript, if the prover should have an idea of the hashing function and the random number, like the sort, at the end of the day, the prover can alter any of the equation to suit what he wants to send back for verification and stuff like that.
The verification. Yeah, but the thing now about hash functions is that they are deterministic, right?
Yeah.
Because the verifier, you cannot reverse exactly. And even if you want to reverse, it may take you years, right?
And maybe reverse or you're guessing.
Yeah, it will be random guesses, so it will take years. But you get the idea.
Please. I want to know, right?
Okay, sorry. Let me just ask.
I was saying, how does the verifier know the random number that the transcript is sending to the prover?
Is sending to the prover. Hash functions are deterministic, right? So with the proof, the verifier can also append those same messages to the transcript and still sample. And when the verifier samples, the verifier is expected to get the same hash that the prover got, because hash functions are deterministic.
Yeah, so the whole purpose of the transcript is to remove the back and forth movement, but at the overall end, the verifier still does the what's it called? The oracle check Or is it the transcript that does the oracle check?
No, the verifier does the
The
oracle
verifier does
check.
the oracle check. So that means the transcript is just the intermediary for the main time
For the
until you
main
get to
time.
the end, then send it to the verifier to perform the oracle check.
Yes.
But the end now is that point where you only have one variable, right?
Yes.
That's what we describe as the end. So when we get to that point where you only have one variable, that's univariate polynomial.
And we perform the oracle check is the main check of like the Sumcheck
So
protocol.
that means there's some point where it could have gotten to the verifier through the transcript, like the transcript is gone and then use verifier does the oracle check and then it's wrong and then it can initiate the process again.
If it's wrong, then the verifier rejects.
Rejects.
Yes.
Just like discarding the entire basket.
Yeah, the entire like everything exactly.
So who sends the initial polynomial to the prover?
The verifier.
The verifier.
Yes, the verifier.
Initiates the process.
But even
Yeah.
with this transcript, do we still have that round check?
The round checks. Yes. The verifier is going to kind of like replay the protocol. Right. Based on like in the proof is going to contain those univariate polynomials. Right. And the verifier is going to evaluate those polynomials as 0 and 1 when the verifier wants to do the verifier's check. Right. But the verifier also needs to get the randomness for each round. So in order for the verifier to get the randomness that the prover got from the transcript, the verifier is going to need to append the claimed sum and the univariate polynomial to the transcript to act as like randomness, to be able to now sample the random challenge that the prover also got when the prover sampled.
So what's synonymous to trace in the whole Sumcheck protocol, the whole interaction? What can we say is a trace in all of this?
In the Sumcheck protocol, we can.
I was thinking the univariate polynomial.
To be the trace.
Yeah, because that's what like shows each of the steps. That's what it's sending to the verifier. So and each of those univariate polynomial is what links everything back to, we're keeping the 6 and the 10 that the verifier is sending to the prover, and for each of those values the verifier sends to the prover, it generates a different polynomial, right? So those univariate polynomial that the prover sends to the verifier, I'm thinking that could be like the trace of how the processes went from point A to point C before, I don't know, just...
Yeah, those are the proofs. You can think of that, those are the proofs.
Okay.
Yeah. So the univariate polynomial for each round is the proof. So basically the proof, you can think of the proof as like an array of univariate polynomials.
Okay, so
for each round.
I was thinking let's look at it from, if we are looking at, you made an example with Starknet Ethereum, right? So let's look at it from that perspective, where every computation has a proof, just like Cairo, every computation has a proof. At the end of the day, what Starknet sends to Ethereum is like the proof of proofs, like the proof of all those individual proofs that were generated. And what Ethereum is checking is the final proof, is just getting the final proof of all the proofs and validating that, okay, all the steps were taken. So if those individual univariate polynomials are the proofs, are they not the trace? Because that is what makes up the entire final proof that the verifier is checking?
They are not the trace, right? Those ones are the proof. But okay, in the Sumcheck protocol, we can think of the trace as that, like I said, yes, that array. Yeah. That initial. This, you can think of this array as the trace. So we will now need to encode the trace. We need to encode the trace as a polynomial that we can now perform some check over the polynomial. So that's the same thing like in the let's say computation case, right? Where we can think of this as like the first step of the computation, the second step of the computation, the third step of the computation, the answer is meant to be 0. The next step of the fourth step of the computation, the answer is meant to be 2. That type of thing, like each step of the computation, right? So that is what will give us the trace. Yeah, so we're now meant to like summarize that trace by generating a polynomial that represents the trace.
So once we get to Sumcheck, we are not talking about trace anymore.
Yeah, we are done with trace. So the proof now is like the proof that the computation was done correctly, because we have already encoded the computation, which is the trace, as a polynomial. You get, so now we are now working with polynomials. We are done with trace generation. I don't know if it makes sense.
Very well.
Does it make sense? Huh? Okay. So any other question? Rahim, are you still with us? Are you sure? You understand up to the point where you are. Any other question about the Sumcheck protocol, or are we sure?
Yeah.
Yes, sir. Yes, yes, yes.
Okay. So I think like, if no other question, I guess we can